Well, a very, very good morning, everyone. Can somebody just confirm you can hear me okay?
Yeah, I can hear.
Fantastic. That's always a good start if you can hear me. Welcome everyone to our very first lecture of the HSMA 4 program, which hopefully will be a very exciting new program for all of you. So just a couple of points of housekeeping. If I can just ask you to all make sure that you're muted, except where we ask you to interact. And also, just to let you know, as with all of the lectures, this session is being recorded and will be shared on our YouTube channel. None of the breakout sessions will be recorded, which is the main points at which you are interacting. But if you don't wish to become part of the recording, then just be aware of that. Anything you say during the main lectures will be recorded and posted on YouTube. Other than that, though, it's a very warm welcome from me. And really, today is all about setting you up for the course and talking about much of the sort of foundational stuff that is going to be key to a lot of what you're going to be doing over the next 12 months. And this particular module, Module 1, is basically a sort of broad brush introduction to operational research and data science, and also to programming. So most of October is going to be spent with me teaching you how to code specifically in Python. Now, please don't worry if you've never programmed before, because we are going to teach you right from first principles, and that will start with this afternoon session where we don't actually do any hands-on coding, but I show you some of the principles of coding, which will hopefully make everything else slot into place. But today, this morning specifically, we're going to be talking about what is operational research and data science, and we're going to be exploring some of the key concepts and also some of the key considerations that you need to think about whenever you are undertaking an operational research or a data science project. So there's quite a bit of information to go over this morning, and there's a good few sort of interactive exercises as well. But lots to take in. Don't worry if it doesn't all sink in immediately. Essentially, we're giving you the sort of groundwork for you to be able to undertake projects, and these are some of the things that you'll need to think about. And you'll get lots of practice over the course in order to sort of put these things into practice. Okay, so without further ado, let's make a start. So let's start with operational research, which is the OR bit of our name in PENCORD. It's the Peninsular Collaboration for Health Operational Research and Development. So I'm going to explain what we mean by operational research. Operational research has got a horrible name, I will just say up front, because it doesn't really explain very well what it does. So we're going to explore a little bit about what OR is. So we're going to do that using an interactive little exercise, okay? So I want you to imagine that you are in charge of an emergency department and you've been asked to cut costs and very quickly. And basically 2 options have been proposed to get rid of a senior nurse or to get rid of a treatment cubicle. And we're going to imagine, just for the purposes of this simple exercise, that either the costs of each are the same, or more realistically, that both sort of solve your problem. Okay, so both will solve the cost problem that you're trying to solve. So now in your emergency department, patients arrive, they get registered at a registration desk, they then get triaged by a senior nurse, then they're treated in a treatment cubicle, and then they're either admitted or discharged. And for the purposes of this exercise, we don't care. They've exited our bit of the system. Okay, so they come in, they get registered, then they get triaged, and then they get treated, basically. So a really simple system that we're imagining here. So you've got a whopping 3 minutes to have a chat in the chat there, and I want you to come up with answers for these 3 questions. How long, on average, do you think a patient spends in the ED now? I'm going to give you some numbers in a minute. Now, I want you to imagine you've just taken an average, say, over a year. So how long do you think the average patient spends in an ED? What cost-saving decision are you going to make? So you're going to get rid of a nurse or a cubicle. Now, remember, both will solve your problem, but you're wanting to minimize the negative impact, which would be patients spending longer in your emergency department. So you want to make the decision that you think will have the least impact on patients spending longer in the department. And then I want you to say what you predict is going to be the impact of your decision on the average time. So both decisions should increase the average time that a patient spends because you're removing a resource. How much longer do you think a patient will spend in the department as a result of your decision? Okay, and you're going to get 3 minutes, and there's a poll on Slack, which I'll show you in a second. You've probably already seen it in the Common Room channel, and you can submit answers to these 3 questions. So these are the 3 questions. Here's some data that I've given you here. So I can tell you currently have 2 senior nurses, you've got 4 treatment cubicles, and I can tell you that on average, a patient is arriving at the ED every 8 minutes. It takes them 2 minutes to be registered once they're seen at the desk. It then takes them 5 minutes to be triaged once they're seen by a nurse, and it takes them, on average, 30 minutes to be treated once a cubicle is free. So if I show you the poll, so I want you've got 3 minutes, have a chat on the Zoom chat as well to discuss what you're thinking, and on Slack, we go into the Common Room, you should see there's a poll here with these 3 questions, which some people have already voted on this morning. So I hope you're very confident in your responses. But you'll see there's 3 questions. How long on average do you think they spend now? We get rid of a nurse or a cubicle, and how much longer in minutes will the average patient spend in the ED as a result of this? So you've got 3 minutes, off you go. About a minute left, so make sure you get your votes in on Slack. About another 20 seconds, and then we'll have a look at the results. Hey, your time is up. So some interesting considerations coming up in the chat. Some good modeling questions, actually. So this is deliberately a very simplified example, and you'll see why in a moment. And I've deliberately not given you certain information. Let's see what people are saying. We've had 32 responses. How long do they spend in ED now? 90 minutes, 60 minutes. Let's have a look at all the responses. 150, 210. So you're all around sort of 3-4 hours ish. Some more optimistic than others, I guess. I presume that 4.5 is in hours, not minutes. Otherwise, that's very optimistic. Then we've got how will you get rid of the nurse or a cubicle? So it's most people are saying cubicle, but there's quite a lot of people saying nurse. So we've got nearly 40% of people saying nurse, but most are saying cubicle. And how much longer do you think the patient's going to spend in the ED as a result of your decision? Most people seem to be saying about sort of 30 to 60 minutes ish. 3 minutes. That's quite that's optimistic. Well, let's hope so. We never know. So that was really to get you thinking a little bit about a typical kind of OR kind of problem. Oh, sorry, my sharing is not working. Okay, should be able to see that. So what we could have done is to build a model to help us answer this particular question. So there are two kind of key concepts in operational research that are really important, particularly when we're doing what we call discrete event simulation, which we'll touch on in a bit. One of them is something known as the base case scenario. We refer to that as being a kind of model of basically what's happening now in the system. So we create a virtual representation of what's happening in the system right now, and then we can use that to see how well the current system is working, and also try and validate the model, and also try and get some clues about what might be happening in the real world system that might help inform what we might want to do. So in this example, we could use the base case scenario to answer the first question, how long on average we think patients are spending in the ED now, but we could also use it to get some clues about the second question, what cost saving decision we're going to make. It won't be definitive, but it might indicate where some of the problems are. Now, the other sort of power of modeling lies in something known as what if analysis. And basically, what if analysis is where we take our virtual representation of our system and then we play around with it in some way. We adapt that model to try out and test different scenarios. So we can say, what do we think would happen if we did this? And that's where the real power of modeling comes in. So in our example here, we could use what if analysis to predict what might happen if we were to get rid of a nurse or we were to get rid of a cubicle. And that's where the real power of the modeling lies, and it really helps to provide sort of evidence-based evidence to inform a decision, an operational decision, and that's the core of operational research. So in our example, we can use that not only to help us judge what decision we're going to make. It's not definitive. Remember, the decision maker has the final say on that, because there will be things that won't be considered by the model. But it'll also give us some sense as well in our example about what we think the predicted impact is going to be. So we can get some sense about if we did this, we think the impact on ED waiting times would be this, for example. So I said we could have built a model to answer this question, and indeed we have. So let's have a look at it. Now, you are very welcome if you have got everything installed in your Python. Don't worry if you don't want to open this right now, but one of the files that you should have downloaded with the materials for this session was a file called howlongspenddd.py. This is a Python file, which you're going to learn all about in this course. This is a what's known as a SymPy model. It uses a package called SymPy, which again you're going to be taught in this course to create a representation of this system that I've just described. Now, I don't expect you to be able to understand most or indeed any of this at this stage, so don't worry about that. But just to say, you are going to be, within the next 6 to 8 weeks, actually coding stuff like this, and you'll be building models actually more complicated than this. This is a very simple model. But basically, just to take you through, what's happening is we've got a representation of the system I described, where we've got arrivals coming into the system, and then we've got, and they're coming in at a certain frequency, and we've got our patient journey, where they go to see a receptionist to register, and then they see the triage nurse to be triaged, and then they stay in a treatment cubicle. And as I say, this is a very simplified system. We assume everybody is treated, which obviously isn't going to happen in the real world. And then we just assume they leave. We don't care what happens to them in our model after that. They vacate the treatment cubicle, and we stop monitoring them. Now, the real power of building a model in something like SymPy is we can very easily change things around. So I've got this set up here that we've got our free resources, which are receptionist, triage nurse, and treatment cubicle. And you can see the receptionist has got a capacity of 1, so we've got 1 receptionist, we've got 2 triage nurses, and we've got 4 treatment cubicles. And here are the numbers that I plugged in, that I gave to you. So the average inter-arrival time is 8 minutes, registration time 2 minutes, triage time 5 minutes, and treatment time 30 minutes. Now remember, these are averages, and I was very careful to emphasize that. What I didn't tell you is, of course, there's going to be some real world variability. Not everyone's going to arrive every 8 minutes on the dot. Not everybody's going to spend exactly 2 minutes being registered or 5 minutes being triaged. So we will use distributions, probability distributions. Now, we will talk about that later, but basically we'll kind of sample. So we'll take some random numbers that are around those averages. And the shape in which we do that is known as a distribution. And again, we'll cover that a bit later, so don't worry about that for the moment. But basically, there's going to be some variability. So let's run this model and see what happens. So I let that run. Right, okay, so it spit out some results. It says the average queuing time for reception is, well, just over half a minute, so very quick. The average queuing time for triage is about half a minute. So there doesn't seem to be much of an issue around reception or triage, but there is quite a significant queuing time for treatment after they've been triaged. So coming up to 2 hours, which gives the average time in the system about 147 minutes. Now, this is just a single run of the simulation. And whenever we run a simulation like this, we don't just, because we're using random numbers, we don't just take our results from a single run. We usually, in fact, run this lots and lots and lots of times in a batch run, and then take the averages over those runs, because we might have a run of really bad luck where we just sampled some really nasty numbers. So we need to let things even themselves out. And again, we'll talk about that later in the course. So let's run it a couple more times, just to get a sense about how sort of accurate that is. So, okay, it seems about, so the queuing time for treatment has gone down a bit, as is the average time in the system, but it seems to be about the same. It's about 140, 130, 140 minutes. That one's a little bit longer, about 180, but we're getting a sense about what the average might look like. Okay, so that's with our base case. Now, from that, we might deduce that given our two options of get rid of one of our two nurses or get rid of one of our 4 treatment cubicles, that actually getting rid of one of the treatment cubicles may not be the best idea, because we've already got a queue, quite a significant queue, whereas we don't seem to have much of a queue for triage. But we can test that out. So let's first of all, let's have a look. Let's play around with this. Let's see what would happen if we did indeed get rid of a nurse. So at the moment we've got 2. I'm going to just change that to 1, and I can now rerun that model. Let's have a look, see what impact that had. Okay, so as we would expect, the queuing time for triage has gone up. So people are now waiting about 8.5 minutes. That's understandable. We've got rid of a nurse. Okay, so there's only 1 of them now rather than 2. So we would expect a jump. But actually, the overall time in the system doesn't look like it's jumped up much. Let's just run that a few more times just to get a sense of that. Yeah, about 130. Again, not a huge increase. People are waiting a bit longer for triage, but to be fair, they were waiting like half a minute before, which is, given my experiences of ED, pretty quick. So it doesn't seem to have done much other than there's a bit of an extended wait for triage. Okay, let's put the nurse back in. Let's see what would happen if we were to remove one of the treatment cubicles. So I'm going to take them down from 4 to 3. We'll run that model again. I've put the nurse back in. Wow. Okay. That seems to have had quite an impact. So we've gone from an average time in the system from about 2 to 3 hours-ish up to 52,000 minutes. Now, that's quite a jump. Again, maybe possible we just had a really nasty run of bad luck there. Let's just run that a couple more times to see. No, that looks like it's unfortunately had a very, very negative impact. So that, and it's all in this queue for treatment here. So people waiting for the treatment cubicle, now waiting 53,000 minutes. So a huge increase. There's clearly a catastrophic decision if we get rid of one of the cubicles. Now, we could see in the model that when we ran the base case that it seemed that there was a bit of a queue around the cubicle, but I don't know if we had any indication that getting rid of one would have caused that. So what this model's allowed us to do is very quickly knock something up that allows us to see what our system looks like, where the bottlenecks might be, and then to play around with that model to see what would happen if we took certain actions. And again, that's the real core of operational research. Okay. So operational research fundamentally is about applying modeling, simulation, and analytical techniques to help inform decisions and improve decision making. They are just another tool in the armory of decision makers. They do not make decisions, but they provide evidence that can help inform decisions. And indeed, if you were a decision maker faced with that, albeit rather simplified decision, you may have to make a decision based on very little evidence. And in fact, by creating a model with the data you have, you can get a slightly better sense about what might work and what might be an absolute catastrophe. So what are some of the sort of generalized benefits of modeling? One of the key benefits, which we've just talked about really, is the benefit of emulation. So emulation basically means that we can create a version of reality, which is what our model is, that we can change and play around with without risk or consequence. So especially in something like a healthcare setting, or indeed in a policing setting, you wouldn't tend to go into your ED, for example, and say, oh, I don't know what to do. Let's just try it for a week with one fewer nurse or one fewer cubicle. Because if it's a catastrophe, which getting rid of a cubicle would be, that's going to have a real impact for patients and potentially endanger their health and their lives. So modeling allows us to just play around with it in a safe way and get a sense about what might work. There's also the benefit of speed. So a model like that, you can knock up very, very quickly, and a lot more quickly than any real world changes could be affected as well. And so these models can be built very quickly, and you can plug in some data and get a really quick sense about what the impact of these changes might be. Some of the side benefits of modeling are things like communication. So when you're talking about changes to a system, actually having a model as a reference point can help people talk about and communicate about a problem using a kind of shared language and point of reference. So by talking about the system as it's represented in the model, it can help people talk about what some of the issues might be, and by exploring some of the data that you need to parameterize that model, it can help people to understand what some of the challenges might be in making whatever changes are proposed. Kind of going hand in hand with that is the benefit systems thinking. So getting people to think in a systems kind of way can often be difficult, because understandably people are focused on their little bit of the system, their specialism, what they do on a daily basis. And we all do that. We're all guilty of that, because it's just natural. That's what we do. It's our job. We're focused on our bit. But actually, a lot of these changes require sort of a higher level thinking to look at a whole system and how things link in together. And actually, the process of designing a model can help people do that. And it can also help people talk with other people who are involved in that system, and find out what some of the issues might be, and even sometimes solve the problem without actually getting to the model, just by getting people talking. And the final sort of key benefit is one of objectivity. So a model can help provide objective support for an argument. A lot of decisions that are made are always, sort of filled with emotional, political senses. And actually, a model can provide that kind of objective evidence. Say, well, what does the data say? What's the data telling us is likely to happen, and what's going on now? Now, there's a big disclaimer on that, because that assumes the model has been built objectively. You can make a model say whatever you like. So you need to be very aware of that, particularly if you're building a model, that you're being very careful that you're not building in bias into that model. So that's kind of operational research. And that's the main thing that we've been doing for the best part of 10 years now. The other side of what we do, and something we've kind of grown more into over the last few years in particular, is data science. Data science is very similar, but also very different. So data science uses methods from things like machine learning and statistics, data mining, data analysis, to help generate insight from data. So in operational research, we're kind of starting with the system or processes, and we're trying to create a virtual representation of that system. And we use the data to kind of plug into that so that we can run that virtual little virtual playground. And then we can tweak little bits and test what will happen if we do this, and let's chuck a nurse out and see what happens. So we're using data to kind of parameterize that. In data science, we start with the data, not the system. And we use these kind of techniques to try and explore and see if there are hidden patterns or hidden structures within the data that can provide us with new information. So it's basically looking at the data and saying, are there things in the data that can help us to better understand our system? And again, to provide, hopefully, with the aim of providing insight to inform decisions. So an example operational research question might be that we want to make these changes to our process for triaging patients. What do we think the impact's going to be, and what resources are we going to need to make sure that we keep things running efficiently? Whereas an example data science question might be something like, look, we've got lots of data on readmissions. Can we teach a machine to try and automatically identify which patients are likely to be readmitted? So it's similar, but it's a kind of different approach. OR starts with the system, in this case, the system for triaging patients. What if we were to change that process? Whereas data science starts with the data. We've got lots of data on readmissions. Can we find things in there that would allow a machine to automatically identify and flag up to us which patients are likely to be readmitted. So in this particular course, you're going to learn about a number of different OR and data science methods. So specifically in operational research, you're going to learn about discrete event simulation, agent-based simulation, which is my sort of old specialty, system dynamics, which you use to do sort of whole system stuff, geographic modeling, and forecasting methods. And you're also going to look at the following areas of data science, which are primarily things like machine learning and natural language processing, where we use it to explore free text, network analysis, which is a fantastic approach for getting a handle on complex systems, and also doing some analytics using R. So the sort of stuff you guys have probably traditionally done in Excel, but actually using a more robust language for that. Now, to start you thinking about how some of these methods might apply for some of your problems in your own organizations, I'm just going to give you a very quick sort of whistle-stop overview tour of each of these. You're going to learn about all of these things in detail in the modules in the course. But I just want to give you a bit of a sort of sense about what these things are, just to start to get you thinking about this stuff. So discrete event simulation, those of you who came to the HSMA 3 event last week will have seen a couple of these slides. Discrete event simulation basically is a way of modeling queuing type problems. Okay, now they exist everywhere. Everything is a queuing problem because it's anything where essentially you've got people going through processes. It doesn't have to be people indeed, but very often it is people going through processes and they're waiting for resources in order for that process to happen. And so because of that, very often discrete event simulation is used to model pathway problems. So what happens to patients when they arrive at the ED in our original example, or what happens to patients when they arrive at their GP surgery, or what happens when you book in an offender into the local police station. These are all processes. A set of things happen, and at each stage you need some resource, and it might be some person resource or some stuff, or both usually. So discrete event simulation is useful for asking those kind of what if questions about changes to those processes. So this might be an example model where patients are arriving at your ED, they get registered, they get triaged, they might no further action might be taken, or they might be treated, and then they might get admitted. And at each stage, we've got various resources. So we've got receptionists that are booking patients in, our nurses who are triaging, etc. And there's different ways in which they might flow through that system. So it might be that after they're treated, they might sadly pass away, or they might be discharged and need no further action, or it might be that they need admission to the hospital. And we'll look in the discrete event simulation module at how we model that kind of stuff. So to give you a kind of real world example, a project I did a few years back now with Royal Cornwall Hospital was looking at muscle invasive bladder cancer. So bladder cancer is the seventh most common cancer in the UK. About fifth to a quarter of those cases are muscle invasive, where the cancer actually invades the muscle wall of the bladder. And it's pretty nasty when you get the muscle invasive bladder cancer. The 5-year survival rate's only about 50%. And basically, time is of the essence. You really need to identify and treat people very quickly. The definitive treatment for it is cystectomy plus chemotherapy. So Royal Cornwall Hospital Trust approached us and asked if we could basically build a model, find out where the delays were, because they were getting quite significant delays. They wanted to try and speed things up to see where the delays were, and then come up with some ideas about what they might do to reduce those delays. And then we could test those in the model to see what we think would happen. So very standard, simple OR kind of question. As a result of building what was actually an incredibly simple model that just sort of identified the key stages in the pathway and what some of the delays were, we identified there were two key delays. One was the delay in waiting for the results from the transurethral resection of the bladder tumor, and another was the wait to be contacted by the nurse specialist, so basically the patient to be contacted to be told of their results and to discuss their treatment options. And so what they did within 24 hours of these results, we basically went down. So I went and sat in the cafe in Royal Cornwall Hospital with the consultants and said, "This is what's happening." I showed them the model, and I said, "What can you do about that?" And they came up. They basically brainstormed in front of me some ideas that they could try, and I tested them live in the model. And I said, "Well, actually, if you did this, the model's predicting you get a big improvement." And so they put in place within 24 hours some key changes into that, so that they would fast track patients who they suspected to have muscle invasive bladder cancer within 14 days, because actually they felt they were actually pretty good at that. They didn't necessarily need to have to wait for the TURBT, so they would fast track suspected cases. And they'd also get the nurse specialist to speak to the patient on the ward after they had their TURBT, rather than sort of wait for a separate process after. And basically the model predicted there would be a huge impact of doing that. And in fact, we looked at data 6 months after and found that's exactly what happened. They're basically the average time from the patient being referred into the system to being contacted by the nurse specialist to discuss their treatment reduced by 5 weeks for those patients who are fast track. And indeed, it was reduced by 11 days across all patients as well. So it was a phenomenal difference just from a really, really simple model that just took some very simple data that they had, plugged it into a discrete event simulation, and said, well, what if we were just to speed up that bit? What if we got the nurse to do that here rather than there? What would be the impact? And that reduced the time that you had to wait by 5 weeks. That's phenomenal. Agent-based simulation. So agent-based simulation was something that I did for my PhD, something I've always been very interested in. It's basically a kind of simulation method that, rather than focus on the processes and the cues as discrete event simulation, is actually focused on behaviors and the way in which people behave in a system, and the way in which they interact and the things that motivate them. And it's particularly interested in what happens at a population level when you get lots of people interacting in a particular way and behaving in a particular way. What happens at the population level from these complex, from these simple interactions? What happens? And usually get very complex emergent behavior. Now, it's very commonly used in ecology, where very often you know quite a lot about what an individual foraging animal might be doing, how they're motivated, but you don't understand so much about what the colony of animals might be doing. And it's often used extensively in modeling disease spread and outbreaks, and obviously that's something that's that we're all very well aware of right now. And in fact, in the course, I will show you how to build such a model in an agent-based framework. It's also different to what we call conventional mathematics. So agent-based simulation and cellular automata, which I'll introduce you to in the first session of the agent-based module, is actually an alternative to conventional mathematics that can explain things that conventional maths can't. So things like the way in which a snowflake forms, conventional mathematics can't actually explain that, but things like cellular automata can. And in fact, there's some really weird stuff that you see in the real world that comes out of these really simple cellular automata. And we'll get onto that in that particular module. To give you an example of something, so this is from my PhD. I was actually looking at bumblebees and how bumblebees might forage in a landscape that contains both conventional crops but also genetically modified crops, because there was a big concern that people that were growing genetically modified crops, because bees are such significant pollinators and they travel over really large distances, that basically there would be some sort of cross-contamination, and that they would go and sample their nectar in the GM crop fields, and then they'd spread that GM pollen to non-GM crops. So basically, we built a behavioral model, an agent-based model, so there's individual-based modeling in ecology more commonly, to basically see what they would do. So you can model the simple motivations, the energy motivations of the bumblebee, and then see what happens at a large landscape scale. System dynamics is kind of the other zoomed out end of the spectrum there. So system dynamics is basically where you're trying to model usually large scale or complex systems, and you're trying to understand what the structure of the system is saying about the dynamics of that system, what that might mean. So the fundamental principle of system dynamics is that structure determines behavior. So how does the system work together? How does it all slot together? And it's that's of interest. So we have these things called reinforcing loops, for example, which in system dynamics, or you might know them better colloquially as Fisher circles. So you might have an example where we think about our system as the number of people accessing GP services. As they go up, that increases the waiting time to see a GP. And as that increases, the number of sick people in the community goes up, which then increases the number of people accessing GP services, and you get a kind of reinforcing effect where things are snowballing, and that it gets interesting where those things are spilling out into other stuff as well. So that may then cause a spilling out into the number of people attending A&E, and so it helps you to identify kind of problems and where the way in which the system is structured might be causing issues. And you can also get things called balancing loops, which are basically virtuous circles where things sort of balance themselves out. Really nice. I put a link in there that you can check out in your own time. I definitely have a look at this. This is a great story about one of our previous HSMAs who did some great work right at the start of the COVID pandemic using system dynamics modeling to basically work out what the bed requirements would be over time in Devon, to get a handle on what the dynamics of what was happening in terms of the pandemic would mean in terms of the bed levels, and it helped them pre-plan and avoid a kind of disaster in terms of just being completely short of beds at the time they needed it most, and they were able to pre-plan when they needed that resource. So I won't spend too long on that, but just to say, worth checking out that little story. There's a guy called Dave Spencer, and he's always very happy to talk about that work. Geographic modeling. So geographic modeling is basically where we are interested in where things are or where things might be. And using that to predict what might happen. So we might use that to decide where we should put services, or where might patients go if we were to close things, or where we're finding people with certain demographics or certain disease, for example. If things like demand continue to grow, or services were closed, or if this happened, X, Y, and Z. That's the kind of modeling part. And we've done a lot of geographic modeling over the years, particularly my colleagues Mike and Kerry in stroke work. There's a big work program that within our team looking at how we optimize stroke services across most of England, actually. And so some of their work has looked at how you basically try to minimize patient travel time, or how you try to get more sort of care closer to home so that people aren't traveling very long distances. And the beauty of things like geographic modeling is you can create these wonderful maps, which are so fantastically visually powerful and really engaging. And that's a really important aspect of any modeling that you do. And geographic modeling is great for that kind of stuff. And you're going to see how to do that using a couple of packages. One's called QGIS and one's called GeoPandas, and they both create these fantastic, one's Python-based, they both create these sort of fantastic maps that allow you to put some really nice stuff, all free and open source, of course. You're also going to learn a bit about forecasting, so trying to predict what's going to happen in the future based on observations that you're seeing in the past. And Tom Monk's going to be taking you through your forecasting module, and basically where you're trying to predict what your sort of future levels of activity might look like in order to try and plan your services better. And you're going to learn quite an array of different forecasting methods in this course, ranging from the very simple, which often are actually adequate and sometimes better than some of the more complex stuff, but also some cutting edge stuff as well. which use neural networks. And don't worry, you're going to learn all about neural networks within this course as well. Really important point to say about though forecasting the results of forecasting is they're not crystal balls. Okay, so people very often make the mistake of thinking that a forecasting prediction is pretty much guaranteed to come true. That's not the case. They're giving you a kind of indication about what might happen based on patterns that you're seeing in the past. So a really nice example of this, Tom did some fantastic work with the Southwest Ambulance Service, who put together this amazing tool. And I don't know if Andy's in the room, but Andy Main is in the program as one of your trainee mentors. If you do want to speak to Andy about this, I'm sure he's very happy to talk to you about this fantastic dashboard that he developed, which allows the ambulance service to better predict some of their future levels of activity. So do contact Andy on Slack if you'd like to talk to him more about that. That's kind of the operational research stuff, and then moving into some of the data science stuff. Big thing you're going to learn about is machine learning. Everybody wants to learn machine learning now. It's a big thing, rightly so in a lot of cases. I think there's a danger people see it as a panacea and a sort of solution for everything, and I don't believe it is that. But there's certainly a lot of fantastic stuff that you can do. And so there's some really good approaches that you can take to try and get use machine learning to try and really learn more from your data. And particularly in this course, you're going to be learning about things like neural networks and also things like logistic regression that can help you to take real world health and policing data and try and build systems that can really support decision makers. So machine learning is basically all about you're trying to teach a machine to learn something that maybe that you can see, but maybe something you can't even see. Might be stuff that hidden stuff within the data that we can't even see. And we're essentially trying to get the machine to say, look, if the inputs are like this, then I think the outcome is going to be this. So if I see these observations, then I predict that this person has this condition, for example. And there's different types of machine learning. There's things called supervised learning, which is basically where you teach the machine by showing it examples with the answers, and then it gradually it can adjust how well it's performing because it can see what the solutions are and try in the training data and try to improve itself. You can have unsupervised learning, which is usually where you don't have any correct examples. You don't know what the answers are, and instead you kind of chuck this mess of data at the machine and say, look at that, sort that out. See what you can see in here, see what hidden structures there might be, try and cluster the data into certain groups. Will that help us to understand this? And also something called reinforcement learning, which is actually what I used for the Bumblebee modeling in association with the agent-based simulation, which is basically where you model agents who are interacting with an environment using trial and error, and basically they get rewarded and punished. So it's the way animals learn in the real world, that they learn to do things that give them reward and avoid things that punish them. And reinforcement learning is potentially hugely powerful and a hugely important area of AI. So we've had quite a few projects, both within HSMA and within the team, that have looked at machine learning. So we have one in HSMA 2, which is brilliantly titled Artificial Ian, where our HSMA tried to create a virtual representation of a man called Ian, who was basically making all their surgical cancellation decisions to see if they could basically recreate what he was doing. Turned out they couldn't, actually. There's something Ian was doing that wasn't captured. But that was actually really important for them to try and understand what might be, what Ian might be doing that isn't being captured, to try and get them to see if they could capture that data. Also, there was an HSMA 3 project, which those of you who came along last week heard a little bit about, where one of our GPs was trying to teach a machine to predict when a patient was likely to be admitted to hospital based on sort of clues in their GP records. And also a big project, if you want to read about it, again, I've put in a link there. My colleague Mike leads up this work, big funded work that we that we undertake. You try called the Samuel project, which is basically trying to teach a machine to determine when a patient who's had a stroke should receive clot busting treatment to try and help inform clinicians, because a lot of the thrombolysis treatment, clot busting treatment is inconsistently applied across the country, very inconsistently, and actually having an AI to help people say, actually, we think you could thrombolyze this patient, or we don't think you should thrombolyze this patient, can really help inform that decision maker. Natural language processing. So this is my particular area of research interest. Basically, it's taking all that free text stuff that we've got loads of, and trying to find a way to unpick information from it. And we use many of the AI techniques that are sort of commonly used for some of the machine learning stuff in order to do that. Now, natural language processing, there's kind of two sides to natural language processing. The first side is where you're trying to get computers to understand natural language. So when you communicate with a computer, you try to get it to understand what you're saying. So that's things like speech recognition, or building an AI that if you talk to it will give the illusion that it understands you and talks back to you. And then there's the other side, which is basically getting computers to learn how we form our language so that we can automate that extraction of information from free text. And it's that second area that we're going to be looking at within this course. There's kind of three key areas in which we will look at in this particular course as well. Related to that, so things are called name density recognition, which is basically where you take free text and you're trying to extract specific things. It might be the names of people or places or organizations, or the names of a procedure, or whatever it may be. There's things called sentiment analysis, which is basically where you're trying to work out and get the machine to learn whether a piece of text is positive, negative, or neutral. And there's something called relation extraction, which is basically where you are trying to identify relationships between entities, and we put them into something called relational tuples. So again, we'll cover all that in the course, but really powerful methods for actually allowing you to extract that kind of data from free text, which is so powerful and has gone unused in so many cases traditionally. So we've had quite a few NLP projects in the past, a couple in the HSMA 3 program. Again, our GP looking at the GP patient notes, try and extract all important information, important clues that they could then sort of feed into a machine learning algorithm. Looking at using AI that can automatically classify patient surveys about virtual outpatient clinics to determine how people feel about them. We had a project that was trying to look at extracting information from modus operandi text to try and identify links between offenders and their victims. And a previous project that we looked at that is still sort of ongoing, looking at trying to extract information from ambulance crew notes with Devon Air Ambulance to try and automatically identify the kind of procedures that were undertaken without having to manually trawl through all this stuff. Network analysis. This is kind of Sean's real interest. He's got currently undertaking a fellowship that's doing some fantastic work looking at network analysis for health, particularly in the field of mental health. Really good way to try and understand and unpick complex systems and understand how they kind of fit together and better understand those kind of very complex bloated systems that nobody really has a handle on what they're doing. And actually, one of the most fundamental things that you should do whenever you're trying to improve any system is get a handle on how your system works. How can you improve something if you don't know what's happening now? And so network analysis is a really good tool for allowing you to do that. It expresses everything basically as a graph. So you might think of a graph as the service structure, and all the nodes on that graph as being individual services, and then sort of the edges, the bits that link those nodes, as being how patients move between those services, and you can weight them so you can see where patients are flowing, and all sorts of things that Sean will take you through. And it's a really powerful thing that can be applied to so much, because as you may or may not know, any problem can be expressed in terms of a graph. So it's a really powerful way to try and understand things. And also, Sean is going to take you through R. I know quite a few of you have got some experience, at least some experience in the R language. Obviously, it's growing in popularity, particularly in the NHS. currently being pushed quite solidly, which is nice to see. I'm just constantly dismayed at how much, not just in health, but in everywhere, how much Excel is still used to do analytics. Excel is a piece of spreadsheet software. If you take nothing else away from this course, take away the fact that unless you're doing financial calculations, you should step away from Excel. Step away from the spreadsheet. It's not for you. And so hopefully the kind of tools that we are showing you in this course will help you to do that and see that you can do much more powerful stuff, much more stuff that is much less likely to be error prone and open to all sorts of issues by using some of these methods. Having said that, I absolutely hate R. That's not R's problem, it's my problem. I just don't get on with R. I think it's because I think there are two kinds of people, those that kind of come from the stats background that love R, and those that come from the traditional programming background where R just looks like lots of weird arrows. But I know a lot of you like it, and that's good, and Sean is a big proponent of R, and we'll take you through some fantastic stuff that you can do there, but rather him than me, because it's not for me. So if you have R questions, key thing, speak to Sean. He's our man. Okay, I've been talking enough, so it's time to allow you to speak with your groups. So throughout this course, there's going to be lots of opportunity to interact. Some of the lectures will be much shorter than I've just given there. Sometimes you'll have a little sort of 15-minute spurt of lecture, and then you'll go off and do something, and then we'll come back. So there'll be lots of interaction built into this course. And the first thing I want you to do is I'm going to put you into your groups, and I want you to basically first of all get to know each other. So have a chat, introduce yourselves, and I want you to basically just come up with some ideas, have a bit of a brainstorming session about how some of the stuff, some of the methods I've just talked about could be used to tackle problems in your organization. Now that's going to help you to start thinking about potential project ideas. Now I'm not in no way expecting you to be coming up with your project ideas yet, although you may, but just to really sort of toss around some ideas and thoughts at this stage. Just to get the ball rolling, because remember, throughout this sort of training phase, the whole point is to get you thinking about potential projects that you can pitch towards the end of this phase to take as a project in phase 2. That's the real heart of HSMA. Remember, it's about those projects in phase 2 that you will manage and that you will work on, that will make a real change for you and your organization and for your patients, for your service users. So coming up with those ideas over the next few months can be really important. So what I'm going to do, I'm going to give you about, gone over slightly, so I'll give you about 25 minutes and maybe take a 5-minute break. So if we can resume at about 11:05, do make sure you take a break in there somewhere as well to stretch your legs. When we come back, I'm going to ask a couple of the groups to share some of the ideas. So as you're introducing yourselves, it would be worth nominating a spokesperson. So if your group is chosen, they can put forward a bit of your discussion. Now, the way this will work, I've set up 9 breakout rooms. If you are in the Marvin group, you will stay in this main room, so you don't need to go anywhere. All of the other groups, you will see you've got breakout rooms, which I will open in a second, then you will see them. And then you can manually join the correct room. Each one is named after your peer support group. So you simply join the peer support group that you belong to. So do that. You can either take a break now or after. It's up to you, but have a chat with your groups, introduce yourselves, and come up with some ideas off the top of your head about how some of this stuff might be used. Are there any questions before I do that? No? Great. Okay, in which case I'll open up the rooms now. Sharing has been screen sharing has been enabled. You should be able to share screens if you want to do that, or you can just sort of have a bit of a chat on this one. Entirely up to you. Right, let me stop my sharing, and then I'll open the rooms. And I'll be bouncing around in between. Hello, everyone. Hopefully you're all back now. Let me just turn off my subtitles, otherwise I start reading them back to myself, and then we'll just get a kind of weird echo. Let me share my screen as well. Okay, great. Fantastic. So hopefully you've all had a bit of a chance to primarily to get to know each other and have a bit of a chat. That's primarily why we did it, but also just to come up with some maybe throw around some ideas. So just before we carry on, I thought I'd just pick on a couple of the groups just to feedback some of the ideas you came up with, and to do that, I'm going to use what will be a fairly regular feature on this course. In true game show style fashion, I am going to spin the wheel of names, the HSMA 4 wheel of names. So all of the peer support groups are in here. I will spin the wheel, and if it lands on you, then congratulations, you have the great honor of sharing with the group what you've been talking about. This is very exciting. Okay, right, let's spin the wheel. Oh, is it talkie toast? No. I think it's going to be deep thought. It looks like it's deep thought. Fantastic. Many congratulations, deep thought, if congratulations are indeed the right term for that. I've temporarily removed you, so you won't get on the next spin. But can somebody from the deep thought team, I'll just temporarily stop sharing a moment, share what you've been chatting about, please?
So we had quite a broad discussion about some of the things that people wanted to look at. So there was overwhelmingly people who prefer R, which was heartbreaking. The majority wanted to do things with discrete simulation, doing ED modeling, bed modeling, and specific specialities like cardiology. And then there were some people who wanted to do some forecasting projects in predicting RTT waiting lists, especially with the pandemic that's just happened, and trying to eliminate the queues.
Okay, so it sounds like a good mix. Lots of interest in discrete events. Sounds like there's some good sort of pathways there that people are essentially interested in, and yeah, I'd say a bit of forecasting as well. That's great. Okay, let's spin the wheel again. Let's see who our next lucky winner is. Oh, should have kept the screen going, shouldn't I? Here we go. Right, let's go back to the wheel. So we won't have deep thought. Let's spin it again. Need some sort of music here, I think. Some cheesy music. Oh, looks like it's going to be Robocop. Is it going to be Robocop? Yeah, it looks like it's Robocop. Well done, Robocop. Okay, Robocop. Would you please share? That's a very odd sentence. Would you please share what you've been talking about?
Okay, we did struggle to come up with some ideas, but using Mike, who was in the HSMA 3 presentation, he used a model to look through social media to find out what people thought of the police station. I can't remember which police he was in.
Oh yeah.
And then I thought that maybe we could do that, because I work for the Devon CCG and I predominantly work in like mental health. So I thought you could do that in social media and sort of, because you often get people who are kind of crying out for help but not in the right place. So if you could kind of scroll through social media to pick out keywords that might be alarming, then you could sort of like check on those people, do like early intervention. And then there was the idea of finding, I guess, just getting feedback on what people think of your organizations as well, of their experiences in like ED and things like that. So.
Fantastic. That sounds great. I like the using sort of natural language processing for the mental health interventions. In fact, that idea came up early last year as well. It never turned into a sort of project idea, but I think there's quite a lot of legs in that. So yeah, definitely something I think that's potentially worth exploring. I think that's a really interesting potential use of that. Great, fantastic. Okay, I'll stop picking on people for a minute. You'll get away with it for a little while longer. So let's move on. So let's talk a little bit about conceptual modeling and problem structuring. So if you're going to be doing any kind of modeling, and many of you will be in your projects, then you are essentially going to be following what we call the modeling cycle. And it's a way of describing the kind of process, very cyclical process that you follow whenever you're undertaking a modeling project. So basically, we start with a problem, a real world problem situation. And from that problem, we then try to analyze the problem and conceptualize the problem to create what's known as a conceptual model. Now, the conceptual model is kind of like a blueprint, a design for what your model is going to look like, how you're going to translate the real world into a mathematical or computer model. Okay, and so that process is actually really important, moving from real world to what you're going to capture in the model. And I'm going to talk a little bit about that in a moment. Once you've got the conceptual model, you then have to translate that into a formal model, so that you're moving from the design of your model to the model. It's building the model itself, which for many of you is going to be building a model, a computer-based model. Might be a mathematical model as well, but most likely you're going to build some sort of computer simulation. Once you've got that simulation, then you use it to obtain some solutions to your what-if questions, test out your scenarios, use the model to obtain the results you need, and that gives you a solution, and then that solution gets hopefully implemented to solve the problem situation. Now, this is by no means a linear process. And you will find yourselves going back and forth between these things all of the time. As you gradually build up the conceptual model, you'll be talking with stakeholders and gradually iteratively building a picture of what the real world looks like, so that you can gradually improve what you need to put into your design of the model. And the same with going from the design of the model to the actual model itself. And all throughout this process, you're sort of going back and forth. It's an iterative process where you're constantly going back to the people who own this problem to find out how your model is representing things, other things you're missing, getting early results out of the model to find out, what this kind of thing is saying. Does this look right? And if it doesn't, why? Why do you think it's not generating the results you expect, etc. And throughout all of this, there's the concept of validity, where you're validating these aspects of your conceptual model. Have I captured enough from the real world? Have I translated my design correctly into my computer model? Have I managed to generate the model and the solutions that I need, etc., etc. So very much today, we're going to be focused on this little bit here, which is the very important bit where you're moving from the real world problem to the design, the conceptual model. So part of that process is really trying to understand and unpick what this real world problem looks like and what you need to capture in your model. So one of the key things that you need to think about when you're doing that is to ask yourself what you're trying to achieve by building this model. Why are you building the model? Okay, and it seems like a really obvious question, but it's actually very, very important to think about that. And there are ways in which you can try and structure that thought process. So think about what the problem statement is. What if you had to state your problem very seriously, very simply? How would you describe the problem? So your problem statement might be something like, there are significant delays in referral to treatment. That might be your problem statement. So that's the thing that you're trying to build a model to try and solve, or provide some evidence to help a decision maker solve it. You need to think about your what if question. So what are the things that you want to ask of your virtual representation of your real world system to try and get that evidence? So it might be that you say, well, what if we reorganize the testing priority? That might be an example of a what if question. What are the questions that you want to ask of the model? And that will help you determine the scenarios that you're going to test in your model. Think about the deliverables. What are you going to give the stakeholders? It might be, a report that outlines what you did and what the results are. It might be that you actually give them the model itself. It might be that you give them the tool to play around with, and that might be the output. But think about the things that you're going to deliver as a result of this project. That's going to be really important when you're thinking about your project work. What are you going to give? What's going to be the output of this project? And really crucially, thinking about what the impact is going to be. So it might be that by doing this project, hopefully you will save lives, or you will meet the target, or both, or whatever it may be. Now, all of the projects, and we will talk more nearer the time about your projects, but what we're looking for in terms of good, solid HSMA projects are, there's a number of things that we look for, but one of the key things, probably the most important thing, is what's the impact? Why should we care about this project? What difference would it make? Because we within PennArc, our organization is judged entirely, quite rightly so, by the impact that we generate. What's the point of this research? What's the point of this capacity building, this training that we're doing? And the point should be that it's making a real difference for services and their users. Okay, so that's a really important consideration. If you're doing a project and you can't really express what the impact would be, then you may want to think about whether that's the right project. Another really important consideration when you're trying to design a conceptual model is to think about the scope. Okay, so it's really important, and it's a really common mistake when you're new to model building, to think that you have to model everything. In fact, usually the opposite is true, because actually the more you model, the more wrong you are, because every model is a simplification of the real world, and there will be things about it that are wrong. Okay, the more you put in there, the more wrong you can potentially be. So you're always trying to look at, basically, what's the simplest model that I can build that will allow me to sufficiently answer this question. So, a typical thing might be that I need to model my emergency department, but then you might think, well, a lot of them are arriving by ambulance, so should I build a model of the ambulance dispatch too? And you'll find yourself going down this sort of spiral of trying to chuck in everything. Now, there will be some things that you will need to incorporate that aren't in your immediate system. So modeling an ED, very often you need to think about what's happening at the back end, because there are back end blockages in terms of the patients being discharged and such. And you may not model that in detail, but you probably want to represent that in some way. But you need to define your scope. You need to define where the boundaries are. And these two key questions will help you. What's the minimum you can model to answer your question? And if I do need to model other systems or other bits of systems, how can I simplify their representation as much as possible? So you're always trying to model the minimum and the simplest that will allow you to sufficiently answer the question. And those are really important things to consider. Similarly, as well as thinking about the scope, sort of how wide you're casting your net, you also need to think about the level of detail. So whatever you are modeling, how much detail do I need to put into the model? You might consider a very low-level model. So you might think about an example here where the patient queues, and then, well, is it a Monday or not? Well, if it is, then Julie's going to put in the books in the patient using the red folder. But if it's not a Monday, well, is it an odd-numbered month? And if it isn't, Julie will do it. But if it is, then John will do it, and that will be using the blue folder. But it may well be that it doesn't actually matter, because Derek's going to collate all the folders anyway, and that has no bearing on what you're trying to answer. So be very careful about going down the rabbit hole of putting in details just for the sake of it that don't actually impact anything. Sometimes, to build stakeholder engagement and trust, you do sometimes have to put in things that will not make a difference, but that people will not trust and engage with the model if they don't think those details are being captured. So you either need to have a conversation about why that doesn't matter, or sometimes you need to put things in. But generally speaking, you want to avoid putting in detail where it's not needed. Of course, on the other end of the spectrum, you might think about a very high-level model where you might say, well, patient arrives, they get triaged, seen by the doctor, and then they're either admitted or discharged. Now, that'll probably be too simple a model, but at the same time, it may well be that's exactly what you need. And in fact, I've built almost exactly that model before, and it all comes back to the question that you're trying to answer. Is that level of detail sufficient in order to answer my question? So again, it comes back to these two questions. What's the minimum you can model to answer your question? And if I do need to model other bits of the systems, how can I simplify their representation? And those key questions, keep asking yourself all the way through the conceptual modeling process. Assumptions and simplifications are key elements whenever you're designing any model. And all models will have both assumptions and simplifications. Now, assumptions are basically things that we have to assume because we don't or we can't know their real world properties. And you'll make lots of assumptions when you're modeling, and that's fine, as long as you're very clear about the assumptions that you're making. So it might be that we're making the assumption that the data that we're using to plug into the model is representative, that it's decent data. We might be assuming that there are no travel times within the clinic for staff or patients, or that they're trivial. So we're making a number of assumptions, and as long as you declare that and declare what you're assuming, then that's fine, because people can understand the results of the model in the context of the assumptions you're making. And sometimes people will then challenge that assumption and say, actually, no, there are quite significant travel times because the patient's over here, there's a 10-minute walk going over here, which is going to impact our system quite significantly. So you may say, well, in which case we need to capture that. We'll need data that we can then plug in, that we can put that into the model. Similar but different simplifications are things that are in the real world, but which we choose to distill down into a simpler representation because we don't think that adding in complexity is going to provide any benefit. So an example might be that if we're modeling a triage process, we just say, well, that's a process in the model where the patient basically holds on to the nurse for a certain amount of time and then the nurse is released. And that represents our triage process. And in most cases, that's the kind of level of detail you'll be dealing with. But sometimes there might be really important things that go on there that you need to capture. But usually you're going to be making simplifications like that. Or we might think about things like, we simplify such that there are no limits to the queuing time for the MIU. Now, obviously, in reality, of course, there will be. People wouldn't, if your model predicted that there was a 30-day wait, with people waiting in a waiting room for 30 days, that's not going to happen. But that simplification might be important in the model because it might allow you to say, well, look at the ridiculous times, and that's going to cause hidden queues and hidden problems with our system. So it goes back to this point, and you need to keep remembering that all models are wrong, and they are wrong because they are simplifications of reality. They miss out and ignore bits of the real world. And in the natural and physical sciences, some models are extremely accurate predictors, even though they are simplifications. So I said earlier about the fact I did my PhD in bumblebee foraging. I still remember we did an empirical study where I basically stood out in the field for a week watching bumblebees. It was great fun. It was great fun just standing there for sort of 6-7 hours a day, just watching bumblebees dictating into a voice recorder. Oh, this bee's arrived. I think people who were on campus thought I was mad, completely mad. I probably was. But what we found from that was that our model and the empirical data matched up ridiculously well. I mean, so much so I remember my supervisor saying, could you check that again, because nobody's going to believe that the model's that good. But you very often find that, particularly with natural world systems, that actually they're very, very good predictors of what happens. In other areas, such as the stuff you'll be looking at in healthcare or policing, you might be able to find that your model is sort of indicates generally what would happen, but they may not be very, very accurate predictors of exactly what will happen. But despite those limitations, some models are still useful precisely because of these limitations, because they are simplifications of reality, that you are distilling down that real world complexity and putting it into a more manageable way. So this is an example of a model, the London Underground map, the tube map. This model is wrong. That is not an accurate geographic representation of the London Underground. In fact, that is an accurate representation of how the lines actually look. But it's really useful because the one on the left is much, much easier to read than the one on the right. So it allows people, it's designed with a purpose to allow people to identify where, which tube lines they need to get on, which trains they need to get. And so it distills down and simplifies this real world reality into something more manageable. This is an example. This is a model that is wrong. This is a model of a cardiac ICU with infinite capacity. That's clearly wrong. No ICU has infinite capacity, anything near it. But an infinite capacity model can be really useful because it can allow us to explore the trade-offs between beds and bed blocking. and say, well, if you had this many beds, we think the probability that your beds are going to be blocked are this, etc., and exploring that solution space. Now, in terms of simplification, models often come in kind of two flavors. You get very simple models that kind of give you a feel for the direction of travel, what generally speaking is going to happen. And then you get very high fidelity models that try to tell you exactly where you're going, what time you're going to get there, and all the details in between. Now, as a user, and indeed most of you will be creating models throughout this course, it's your job to distinguish between the two and ensure that your results aren't misrepresented. So if you develop a simple model, which most of you are going to do, that when you convey those results to the stakeholders, they understand the limitations. They understand that when your model says that if you get rid of a nurse, the impact is going to be less than 10 minutes, or it doesn't necessarily mean that it's going to be exactly 8 minutes. And that people will keep going. And if they misunderstand that, they will come back and they won't trust your model. So you need to be very clear about what this is saying is, if we get rid of the nurse, we think the impact would be minimal. But actually, if we got rid of one of the treatment cubicles, we think we'd have a disaster on our hands. So whenever you're trying to build a conceptual model, you need to try and understand the processes that are going on in the real world system. And a really useful tool for doing that, particularly if we're developing something like a discrete event simulation, is process mapping. And process mapping is basically just a way of trying to capture those kind of discrete processes within a system and what the inputs and outputs are to each of those processes to try and understand how that system works. And it's a really vital tool whenever you're doing most modeling, and particularly anything in discrete event simulations, a really important first step. Because as I said earlier, how can you possibly go about trying to improve the system if you don't understand what it looks like right now? You have no baseline to understand if you've improved anything. You don't really understand what you're changing because you don't know what it looked like in the first place. You need that understanding of what the system looks like. So we keep talking about processes. Let's think about, in very specific terms, what we mean by a process. Now, processes are basically activities, stuff that happens, where you have a number of steps and which transform one or more inputs into one or more outputs. And so if we think about a process in that way, we can think of it a bit like a function. A function is something where you have one or more inputs, the function does something with those inputs, and then it generates one or more outputs. So whenever you're doing some process mapping, the key thing to bear in mind whenever you're doing any process mapping to try and translate your real world system into your conceptual model is to bear in mind this very simple rule: always listen to Roy Walker. Say what you see. That's what you need to do. You need to express exactly what is actually happening in the real world system. Not what should be happening, what is really happening now. That's what you need to capture, and that will help you to design your model. So beyond listening to Roy Walker, which of course is a general tip for life, you should also follow these general tips. So whenever you're doing any process mapping, make sure you've got very clear start and end points, and you may have more than one of each. There may be more than one way in which people can come into a system, and there may be more than one way in which people can leave a system, and that's fine as long as they're very clearly defined. So think about the different ways in which people, or whatever your entities are, can enter your system and which ways they can leave your system. And remember, the points at which they enter and the points at which they leave will be defined by your scope, i.e. what's the chunk of the real world that you're modeling, and that will help you understand where the start point is and where the end point is. Describe what really happens, not what should happen. As I say, that's a really important point whenever you're doing any process mapping. Make sure you capture warts and all exactly what's going on in the real world. Having said that, don't worry too much about little sort of one-off exceptions to the rule, unless they're very important. Maybe sometimes your question may be centered around those one-off exceptions, and so that actually they're really important, but usually they're not. So if usually this thing happens, but 2 years ago that thing happened, but it's never happened again, you don't need to worry about that kind of stuff. You should always process map as a team. You will find that quite surprisingly, people have very different perceptions about what the real system they work in looks like. I mean, very different. You can get very surprisingly conflicting responses to the same questions. So it's really important you get more than one person's input, because you will find if you just have one person doing it, you may not be getting an accurate representation of what's really happening, and you might be drifting back to what should happen or what this person perceives is happening. When you're process mapping, you should think about doing it from the perspective of the journey of your entities, so patients or test results, whatever your entities are. How do they flow between processes in your system? What happens to them at each stage? What are the different ways in which they can sort of branch off to different processes? And you should create a visual representation of your system that captures all this, and that's your process map. And that's going to be a really important document that will help you move from the real world to your conceptual model. And you're not going to capture everything in that process map in most cases, but it'll help you understand this is what the real world system looks like. What aspects of that do I need to capture for the model to answer the questions that we need to answer? So here's an example process map where we did many years ago, looking at some cardiology work in Torbay, and it tries to capture that real world system. And again, nowhere near all of this would be used in the model, but it's just a way of trying to understand the real world complexities and then help us zoom in on what we need to capture and what we can drop. So the key thing to say process mapping, I mean, there's no sort of single right way to do it. And in fact, whatever works for you as the model builder and for the stakeholders in terms of getting them to talk about and express what the real world system looks like is the right way. Okay. Commonly though, when you're doing process mapping, it's very common to use elements of flowchart and nomenclature as a kind of framework for building up a process map, because it allows you to capture things like flows and processes, decisions, starts and endpoints that are very common in process mapping. So we could use this kind of format where we mark the entry points and exit points on the system, our boxes here to represent activities, processes, sub-processes, things that are done. And then our diamonds here to represent decision points where things may flow off in one direction or another. And then the arrows showing the direction of travel between these things. And sometimes you'll have bidirectional travel where things can flow back again. And these little sort of notations on these arrows to say that these are the circumstances in which people will flow down this route. Another thing that you should be aware of whenever you're doing any modeling or any data science indeed, are your stakeholders. Remember, all of the work you're doing is to try and solve a real world problem. And therefore, because it's the real world, there will be people who have an interest in and or an influence on that problem and or its solution. And it's really important to think about not only who the stakeholders are, but what their interest or influence level is, because you will need to think about how you engage with those people in different ways. So if you're trying to think about who your stakeholders are, these questions can help you think about identifying them in the first place. So think about who owns the problem. Think about who might benefit if this problem is solved. Crucially, also think about who might suffer if it's solved. If you solve this bit and improve the efficiency of this bit of the system, is that going to have a knock-on impact over here, or is it going to mean that certain staff are being asked to work in different ways that they may not like? So you need to think about that as well. Think about who's got a legitimate interest in the problem and or its solution, and who might have the power to influence the process of solving the problem and implementing the solution. So who's got the power to actually put this stuff into practice and make sure it happens? So why is it important to think about these people? Well, you need to know who holds the information and or the data that you're going to need to build your model. These are the people you're going to speak to. And throughout your HSMA project, you're going to need to be speaking to people who know about these real world systems and who are on the front lines of these systems to find out what actually happens so that you can get a good understanding of how things work to put into your model. You're going to need to know who might help or hinder this project in terms of solving the problem and implementing the solution. And you're going to need to understand the nature of any conflicts or what might be potential conflicts, how that might impact the work and how you might mitigate against them. So you need to be aware of any potential problems that some of your work can cause and how you might protect against that and do things to help engage people with the process. So one way in which you can identify and map your stakeholders is to use something called an interest influence diagram, which is basically where you kind of identify your stakeholders, then you plot them on this little 2D graph where you've got interest on one axis and influence on the other. And you can plot people who have, very high interest or low influence, or vice versa, etc. And by then separating that into 4 quadrants, so people who are both very interested in this project and very influential, you would deal with very differently to those who aren't interested in what you're doing and can't do anything about it anyway. And so these 4 different groups of people you can deal with in different ways, and the way in which you engage with them during a project will differ. And so it's important to think about who falls into those categories. And indeed, sometimes you may find that you have stakeholders who sit in one location, but then because of the actions of the project or because of certain risks, may move into another. So one example is members of the public who may not be particularly interested or influential over what you're doing, but then if it becomes potentially quite controversial, they could suddenly become not only highly interested, but also speak out about it and become influential and put pressure on people, and they can suddenly transition from one quadrant to another. And so you may well need to be aware of some of those risks. And generally speaking, the people in each of these quadrants, so you deal with in different ways. So it might be your key players up here, those that you're going to be engaging with the most through your projects, are those who are really interested in what you're doing and highly influential, will help you actually implement this work. Compared to those who are not interested and not influential, you tend to monitor, as I say, just in case they move into one of these other groups, and think about situations that might cause that. Those who are really interested but not that influential, you tend to keep those people informed. So they're interested in what you're doing, so they want to hear about it. And those who are not that interested but could be very influential and could, put a kibosh on what you're trying to do, you tend to want to keep those people satisfied. And then we just simply map the various stakeholders that we identify onto that map. Okay, time for me to stop talking again, and time for you to go back into your groups. So in the course materials for this session, you've got a PDF file called exercise_2. In this file, it gives you an example of a largely fictional problem, although I will say it is also based on a real-world project that I did a few years back, quite highly based on that. And so what I want you to do for the next 30, let's say till 12:05, so about 25 minutes I'll give you, I want you to look through that problem, and as a group, I want you to identify what the what-if questions are in this problem. I want you to build just a very simple process map of the base case system that's being described. You haven't got time to really go into the ins and outs, so just come up with a very relatively simple representation of that system. And I want you to build an interest influence diagram based on the stakeholders you think you'd need to consider if you were undertaking a project based on that fictional problem. Now, because you're fairly tight on time anyway for this, you may want to split off so that half of you do a bit of the process mapping and half of you do a bit of the stakeholder stuff. Because both of those are a bit more time consuming. Again, don't worry going into too much detail for these things, but I want you to just have a bit of practice taking essentially a real world problem and translating that into, well, what are the questions I can draw out from that might be my what if questions for a model? What does the process look like? And who might I want to engage with? And again, I will spin the wheel of names when we return and ask a couple of groups just to feedback on that. Okay, any questions before I split you off again? Great, okay, I will open up the breakout rooms again. As I'll dip in and out of your rooms and have a listen in, so please do just ignore me and open up your exercise 2 PDF files and have a read through, and then have a chat about it as a team, and see what you can come up with. It may be, if you're going to do the whole lot as a group, I would probably advise doing this first bit and then moving on to the stakeholder bit before going on to the process map, because this is almost more important for this particular bit than the process mapping. But see if you can have a go at a bit of this as well. Okay, great. I will open up the groups now. Towards your back now. So apologies, I could see quite a lot of you were still in the midst of it, so sorry for sort of breaking that off. It's always tricky on this first session because there's quite a lot of stuff to get through that you can get quite involved with. Something, I mean, it's entirely up to you, but something that some of our groups did last year was they had a little practice outside of the sessions and sort of got together and finished this off. It's obviously up to you, but you might find it quite helpful, particularly as you move into your project work, to have a practice on this. But the main point was just to give you a bit of a sample about taking a real world complex problem and trying to translate and unpick that into something that might help you form a conceptual model. So let me just share my screen again. And it's time to spin the HSMA wheel of names, which you'll all come to dread, I'm sure. So I'm not going to pick on the same groups as before, so you will remain removed. That won't always be the case. Don't think you'll automatically get out of things in the future. But let's spin it again. See who we've got this time. Oh! It's Master Control Program by the look of it. Yep. Hooray. Okay, so somebody from Master Control Program, do you want to share your screen if you've got anything?
I'm not sure if that would be a good idea. It's a bit messy.
Okay.
So I might just talk you through
That's fine.
our answers to the questions. Is that okay?
Yeah, that's no problem.
I think I can do that with words, hopefully. So in terms of identifying what the problem is, it's the lengthy waiting times and finding out what's causing those. In terms of what we can change, so the clinic has suggested adding in a nurse specialist to work alongside the doctor to see if that will reduce waiting times. And then in terms of what we can offer the stakeholders, so we said a report which basically shows how the effect of adding in a nurse specialist might change waiting times. And we also said that it would be quite nice to provide a sort of dynamic visual of the discrete event simulation map, kind of showing the state of the system as it normally runs, and then what would happen if you added in the nurse specialist, what would happen to waiting times there. One thing that we just noted here was, this kind of comes back to your point about including only information that represents normal system functioning. And we were saying that the clinic thinks that one of the issues here is that the doctor gets pulled out frequently, and that might not be necessarily modelled in the sort of perfect system flow diagram, but it's really important here because they think that that might be a key factor in determining why wait times are high. Good, yep. So yeah, that's the questions, and then should I go on and talk about the influence?
Yes, please do.
Yeah, stakeholder map. So the two extremes we've got in terms of high interest and low influence, we've got the patients, obviously. And then in terms of high interest and high influence, we thought the clinic administrator would be the one there with sort of the most invested. And then around that, we've got clinic clinicians who are maybe slightly below the clinic administrator in terms of interest, but also have quite high influence. And then we talked a bit about the sort of people that are auxiliary to this system, I guess, like the technicians, the opticians, maybe other clinicians who might be of sort of low interest, but might actually have high influence because they might affect how this part of the system works. So I think that summarizes everything that we spoke about there. And then in terms of the process mapping, we were one of the ones desperately trying to scrabble around and finish. But we identified our entry point as obviously a patient arrives at the clinic. The first activity that they experience is the triaging. And then they enter into a decision point as to whether they see a nurse and are then sent home, or whether they see the doctor, and that's about as far as we got.
Well, it sounds like you had a really good chat there, and lots of stuff covered. So no, that all sounds great, and yeah, really nice point you made there about the in this situation, it's where the odd thing that's happening where things aren't supposed to be part of the process but are happening is actually really important here. And that's a really nice observation. So fantastic. Okay, in the interest of time, I will plow on so you can all breathe a sigh of relief for the moment. The wheel is being put back away for a second. Don't worry, there's more exercises to come this afternoon. So I'm going to try and whiz through this this last bit as quickly as I can, because I want to give you an hour lunch break. So we've got just less than 20 minutes that I will rattle through this. I'll get through as much as I can. Let's talk a little bit about distributions. So I mentioned earlier this concept of variability right back at the very first little exercise you did. So let's imagine we want to build a model of an ED department and its triage process, and we know that patients are arriving on average every 5 minutes. Now, one way we could approach this model would be to basically tell the model every 5 minutes of system time, just put in a new patient into the model. Now, let's also imagine that the time a patient takes to be triaged is also on average 5 minutes. And again, we could just plug into the model and say, well, let's just say that a patient spends 5 minutes with the triage nurse. That's right on average. All sounds perfectly reasonable. Indeed, I have seen models like this built in the NHS. So this is must be reasonable. Let's have a look, see how this would pan out. So let's imagine patient 1 arrives at 7 a.m. They're seen by the triage nurse, and they spend 5 minutes with them, and they finish with the triage nurse at 7:05. Patient 2 then arrives at 7:05. Because they arrive 5 minutes after the first patient. They're immediately seen by the triage nurse, who's just finished with patient 1, and they finish at 7:10. Sometime later, patient 73 arrives at 1 o'clock. The patient is delighted. There's no queue whatsoever to see the nurse. The nurse isn't looking too happy, but nonetheless, they get seen straight away. They finish with the triage nurse at 1:05, and then patient 74 comes through the door. This all sounds great and wonderfully efficient, doesn't it? Although perhaps the triage nurse isn't quite so happy. The problem is this isn't really a very accurate model, because that's not the way in which the real world works. Patients may well arrive on average every 5 minutes, and they may well on average spend 5 minutes with a nurse. But that doesn't mean that every patient comes in at 5 minutes on the dot and spends exactly 5 minutes with the nurse. That's not how the real world works. We haven't accounted for variability. So let's imagine 2 scenarios. In the first scenario here, we're just using our fixed times, inter-arrival times and triage times of 5 minutes. On average, we've got 5 minutes triage times and 5 minute inter-arrival times, but everyone is taking exactly 5 minutes with the nurse, and everyone is arriving in 5 minute intervals. Let's imagine another scenario where we account for variability. So the average triage time and the average inter-arrival time is still 5 minutes, but we recognize that not everyone will spend exactly 5 minutes with the nurse. Some may, but then somebody may spend 4 minutes with the nurse, and somebody may spend 6 minutes with the nurse. You might have an odd case where somebody takes 15 minutes with the nurse. And similarly, patients don't arrive every 5 minutes on the dot. Some might arrive 5 minutes after the other patient. Some might arrive after 6 minutes, some after 4, etc. So if we look at the first scenario where everything is fixed, we'd say here that after 5 patients, it's 8:25. If we're starting at 8. And in the second scenario, we've got exactly the same mean inter-arrival time and the mean triage time, but here we've already gained, lost a minute in those first 5 patients. And that's just with a very small amount of variability. And here we can see that in the 4th patient here, because they arrived in after 4 minutes after the previous one, and because the previous patient took a little bit longer with the nurse, there's a bit of waiting time, which our first iteration, which said that everything was fixed, predicted there were no waiting times whatsoever. And so clearly, by accounting for some variability, we're getting a more accurate representation of what's happening. So because the real world is full of variability, we need to account for it. And the way in which we do that using models is using something called distributions. And basically, a distribution is just a way of trying to represent variability within our data. What it's trying to do is it gives us an estimate of the probability of a particular value occurring in the future. So we might, for example, have a distribution that says that 30% of patients in the past have spent 6 minutes with a nurse. Because our model is going to be, most of the models you build will be stochastic models. That is, they will use random numbers. And so each patient that comes in, when it gets to work out, the model needs to work out how long it's going to spend, that patient's going to spend with the nurse. And what it'll do is it'll sample from a distribution. So it'll randomly pick a number, but it'll take it from that distribution. And in this distribution, we're saying that 30% of patients spent 6 minutes with the nurse in the past. So there'll be a 30% probability that the number the model picks for when it's determining how long this patient spends with the nurse is 6 minutes. That'll be a 30% chance of that. So the distribution basically sets up the probability profile to say there's a X% chance that they spend this long with the nurse. And that allows you to account for like odd exceptions where sometimes you get something where a patient comes in and they've spent half an hour with the nurse. Is a very complex case, something unique that doesn't happen very often, mainly happen in 0.02% of cases, but you can account for that. You can account for that variability. And so you can set up a probability profile that says, well, in 0.02% of cases, that's what happens. Now, you can set up your distributions to exactly match your data. So you can calculate your data and say, okay, well, 27% of patients spend 6 minutes, so I'll put that in, and 31% of patients spend 7 minutes, etc. You don't tend to want to do that though. And the reason for that is that you can end up with a problem known as overfitting. This is a issue that you'll see many times, particularly in the machine learning module, where essentially you're overfitting, you're assuming that your sample of data that you've got is fully representative, and you're putting everything on that data. And actually, a better way usually of doing this is to use a standard name distribution, a particular distribution that has a certain shape and characteristics, and say, well, my data seems to look like one of these distributions. So I'm going to assume that I'm making one of my modeling assumptions that actually, if I had all of the data about all of the patients that would ever come into this service, that actually it would follow this shape, because that's the shape it looks like. And there's various methods that Sean will show you later in the course about how you can do some distribution fitting to actually see statistically what your data most closely resembles. You can also very often see these things by eye, and there's also a couple of key distributions that are very often used for the kinds of stuff that you're going to do as well. So each distribution is defined by either 0 to many parameters, and these parameters essentially define the skew, the range, the general shape, and what it looks like. So here are some examples of some common distributions that you will come across. In particular, the exponential distribution and the log-normal distribution are two very commonly used distributions within discrete event simulation when you're modeling pathway processes. So you will find that you will use these a lot. And in fact, if in doubt, using these distributions will probably give you a pretty good representation. So exponential distributions in particular common for inter-arrival times. That is the time between entities arriving into your model. And log-normal distributions, very common to model process times. You'll find there's also other distributions, so things like the Poisson distribution, which can describe the number of arrivals in a given time, assuming the arrival is at random. The triangular distribution is a pretty awful distribution that I don't tend to like using, but and in fact, I would generally advise you use one of these rather than that. Triangular distribution is basically where you say, you go to your consultant and say, okay, what's the lowest amount of time you'd expect to spend with a patient? What's the highest amount of time? And then you draw a triangle that, and what's the average? And then you draw a triangle with straight lines that estimates that. It's very, very limited. It can be useful if you don't think your distribution, your data is following one of these distributions, but you don't really know, you haven't got enough data to ascertain anything else. But I'd still generally go to one of these. Uniform distribution you will also be using a lot, but for very different reasons. The uniform distribution is basically a distribution where any number within the range is equally likely to be picked. Now, that's not very useful in most cases for process times, because that would say, oh, well, there's an equally likely chance that a patient spends 1 minute with the nurse as they spend 7 days. But it is very useful, as you will see in coding, when you're trying to branch people off, for example, and you want to randomly generate a number that fits into a probability. And we will cover that a little bit later in the course. So some key sort of distributions to bear in mind, but the key thing to take away is that essentially they're probability profiles that are a way of saying my data follows this kind of shape. And so I, rather than saying everybody comes in at X minutes, I will sample each time a patient enters the amount of time that they spend with this resource is sampled from this distribution, where it may well be that around the average it's most likely, but there may also be cases where it's much higher or much lower as well. Another really important thing to consider when you are building any models is the concepts of validation and verification. This is the process basically of testing that your model is doing what it should. Now, there's a slight difference between validation and verification. So validation is basically the process of determining whether a model is sufficiently accurate for the particular objectives of the study. So that's a way of saying the stuff that I've put into my design of my model, is that good enough? Is that design for that model good enough to answer this question about the real world? Or have I made stupid assumptions or oversimplifications? Or I haven't put enough detail in, or I've put in too much detail. Verification is basically testing this bit primarily. So where you're taking your model, and most of you are going to be using Python for your models. So you've typed in, you've basically built a computer program. Verification checks that actually your program works correctly and that you correctly translated what you said you'd do here into a working computer program. And as you can imagine, that's the bit where you'll spend a lot of time, particularly when you're first coding. But unfortunately, that doesn't change over time. So how are some of the ways in which we might want to validate whether our model is a good representation of reality, good enough that it can answer our question? So one simple approach is to use something called black box validation, which is basically where you say, I've built a model of this system, and the model predicts that there's a waiting time on average of 6 minutes. And in the real world, I see that it is about 6 minutes. Therefore, my model is valid. Now, that's one way to approach it. And in fact, that's one of the things you may want to do in your model. The problem with black box validation is that it ignores what's actually happening in your model. So it may well be that your model has indeed correctly predicted that it's 6 minutes, and that's what's happening in the real world. But actually, it's done that by complete fluke. And in fact, it's if you were to approach a different problem with this same model, you'd find that you get all sorts of issues because it's not actually working the way you think it is. Also, how do you validate a what-if scenario? These are potential future scenarios that haven't happened yet. So unless you've got a past historical example that you can compare against, how are you going to check whether the results that you're predicting for a what-if scenario are actually valid? And also, often your real-world data that you're checking against is just either inaccurate or it may just not be available in the first place. So it's a good start, but it's not enough. So we also need to think about validating smaller parts of the model, taking the model piece by piece and checking to see if this part of the ED model, whether we capture the triage process, is that a good representation of what's happening in the real world? We should validate our input data, think about what's the quality of the data that's being used to drive this model. And we should work really closely throughout this process with the subject matter experts, the people that know about the system and can comment on what looks right and what doesn't. We can also sometimes compare results to similar and sometimes simpler models. And there's ways in which we can try and assess what we do about the impact of uncertainty. So it's a really important thing to consider that although validation is an important part of the model building process, it is not possible to prove that a model is valid. You can't do that. You can disprove that it's valid. You can show that it is not a valid model because of this, but you can't prove that it is valid. So actually, validation is part of a process in which you're trying to build confidence with your stakeholders that the model and the results that you're generating from that model are sufficiently accurate for the purpose that it was built to address. So going back to the earlier point, is this model good enough that people can have confidence in what it's saying? And of course, confidence thresholds will vary wildly by user and also between modelers as well. So it's really important to consider that you may have a valid model that is actually a very good predictor, but it may not be viewed as credible. They may not trust it. Equally, you may find you have a model that is a load of rubbish and doesn't actually predict the real world very well at all, but it may be viewed as credible, particularly if the model says what they want it to hear. And that's a really important consideration, that people will always generally want a model to say something in particular to back up their argument. And so people will tend to question the model more when it doesn't say what they want it to say, and equally vice versa. If the model says what they were hoping it would, you'll find you'll get very little other than some smiles, some nods, and my goodness, you're an excellent modeler, thank you. Also, don't fall into the trap of thinking that a valid model is the most realistic one. Going back to the earlier point, simple models are often the best, actually. And the final point I just want to sort of make is around the issue of uncertainty. So let's say we wanted to use a normal distribution to represent our process time. As though that's unlikely, you probably use a log normal distribution, but just for the purposes of this, because the normal distribution is simpler to explain. So a normal distribution is basically defined by two parameters, the mean and the standard deviation. So where the middle of it sits and the spread of it. And the mean and standard deviation that we use to define the distribution in our model will essentially be derived from a sample of data from the real world system. We cannot possibly know all of the patients that have ever come into and will ever go into that system. So it doesn't matter how much data we've got, it'll only ever be a sample. And the problem is that, therefore, any estimate derived from that is going to contain uncertainty, because it is just a sample of the true population data. So our sample mean, for example, might differ from the true population because of chance, or because the sampling process, there's something wrong with it. So it might be that we've taken a really good example. Those of you taking data from the last 18 months are probably going to find some very different data to what you would normally expect prior to that, because of the influence of the pandemic and the impact that's had. So it might be that your data is not representative because of the chunk that you've taken. So how do you deal with that? So one option might be to take a bigger sample, but that's not always possible. You might be using all the data that you can. Even if you could, it will help, but it's not going to eliminate all uncertainty. It's still going to be a sample, albeit a bigger sample. Also, if the sampling process itself is biased, then it's not going to help you. And also longitudinal issues. So as I said, the problem with things changing, so the last 18 months will look very different. And basically the last 18 months have mucked up forecasting for obvious reasons. So another way we can approach it would be try to estimate the uncertainty using sample statistics. And there's various stats approaches that you can use to help you do that. But a really nice way that you can approach it is to use something called sensitivity analysis. And basically, this is a common approach you use in models to say, okay, I know my mean time that I'm assuming to spend with a triage nurse, for example. I know that's an estimate, so it could be wrong. So what I'll do, I'll make little changes to that. I'll try adjusting it, and I'll run the model again, and I'll see what the impact of me being wrong is. Because if I make a very small change or even a medium-sized change and actually doesn't change the results that much, it doesn't matter. I may well be wrong on that, but it's not going to affect fundamentally the model results. But if I make a small difference to something and suddenly the results go out of the water and completely change, then that might be more problematic. And so the decision maker is going to need to be aware of that, to say, look, I'm judging it based on, we've plugged in this mean value here, but if we're wrong even slightly about that, the results say something completely different. And so they need to be aware of that in judging how they will use this evidence. And I'm going to show you a very quick example before we break for lunch for that. The other two things, just this is the final slide, just to say, as well as the actual values, there's other ways in which we can be uncertain. So it might be that we might be uncertain about the shape of the distribution, or it might be that the distribution itself that we've picked is wrong, that we're making an assumption about the shape of the data that is wrong. So just to close off before we go for lunch, I'm just going to take you back to that model that I showed you this morning. So this is the model of the ED. Now, remember, we said that the mean inter-arrival time was 8 minutes, and the mean registration time was 2 minutes, and mean triage time was 5 minutes. These are all estimates. I mean, they're completely fictional here, they're completely made up, but let's imagine they are estimates. So let's do a bit of sensitivity analysis. So I'll just run the base case again so we can remind ourselves what it looks like with our 2 nurses and 4 cubicles. So we were getting about average time in the system about sort of 2 to 3 hours-ish. So let's say the registration time, that's an estimate. We said it was 2 minutes. What if we were wrong? What if it actually is truly about 3 minutes? It's only a minute off. Let's run that again. See what difference it would make. And again, in reality, if you're doing sensitivity analysis, you'd run this, hundreds of times for each combination. Okay, so it's gone up a little bit, but that's still within the bounds of what we were typically seeing. See, the queuing time's obviously gone up, but it's about the kind of numbers we were seeing before. So it doesn't seem to have made a huge difference. So I'll put that back to 2. Now let's say the inter-arrival time. So this is how frequently patients are arriving. We say 8 minutes. Let's say, again, that we're slightly wrong. We could be a minute out on that, at least. Let's say actually they're arriving a bit more frequently. They're arriving every 7 minutes. So a bit more frequently in the model. Let's see what would happen if we were slightly wrong about that. I'll just run that again. Yikes. Okay, seems we've got a problem. Let's run that again, just in case it's just a particular run of bad luck. But no, look what's happened. So this says we might be wrong about the registration time, but it doesn't appear it's going to make too much difference. But you know what? That estimate we've got that patients on average are arriving every 8 minutes, if we're slightly wrong, even slightly, and actually they're arriving every 7 minutes, then our model results are blown out of the water, because suddenly we've gone from estimating 140 minutes to 146,000 minutes in the system. So that's an example of a parameter estimate that we're making that is where the model is highly sensitive to that assumption. So it's highly sensitive to that estimate of our mean inter-arrival time. And that's very important information. Now, in reality, you'd probably then want to see if you can get more information about the inter-arrival times and to really drill down on that. But at the very least, you need to be speaking to the, when you're conveying the results, you need to make it very clear that what would happen if that is even slightly wrong. And you're also reporting those results to say, well, if we're optimistic by a minute, then actually the results would say this. You need to bear that in mind into your decision making as well. Okay, I'm going to stop talking because we're overrun by 4 minutes. So that's the end of today's lecture. I would advise you to go back through and have a look at these notes in your own time. As I know there's a lot of information that's been conveyed over this morning. But some of these things that you're going to get lots of practice in doing in your project work. So this afternoon, we're going to take a lunch break now till 1:30, so you've got nearly a full hour. At 1:30, we're going to come back and I will keep this call open so you can stay on the Zoom call to save you having to come back in manually. I will pause the recording though. Right, a very good afternoon to you all. Hope you managed to have a bit of a restful lunch and stretch your legs and have something to eat and feeling all sort of re-energized. So welcome to this afternoon session, which is going to be talking about programming. So this morning, we obviously took you through some of the general principles of operational research and data science. And This afternoon, we're going to be introducing you to the principles of programming. So for most of the rest of October, a lot of the stuff now is going to be pivoting to basically building up your coding knowledge, and also doing some stuff around making you aware of some of the free and open source approaches, some of the tools you're going to be using in order to do your coding and to share your code into version control and all the stuff that comes with being a good data scientist. And so really that's what the rest of October is going to be like. And then when we hit November, then we're going to essentially get you to use your newfound coding skills to then start taking you through all those exciting things I talked to you about this morning, in terms of the methods, the operational research methods, and the data science methods. So general intro this morning, then sort of now pivoting to talking to you about coding, building up your coding knowledge, ready to do all this exciting stuff. So certainly looking through your applications, there were quite a few of you who had some coding experience. I was delighted to see a couple of you sort of mention doing some assembler code back in the 80s. You're braver than I am. I was a basic man back then. But yeah, so various levels. But I think pretty fair to say most of you got quite a lot of you got a bit of experience in R, some Python, and some had some experience with C++, etc. But I think most were either a little bit rusty or certainly hadn't that much experience in Python. So apologies if any of this is simple. There's going to be quite a steep learning curve over the next few weeks as you start from learning what coding is all the way up to doing some quite fancy stuff in Python. So it's quite a steep curve, but hopefully this is a friendly introduction to what we are doing. Okay. So I'd like to give particular thanks actually to the creators, to the Atari Corporation, because back when I was just 4 years old, back in 1985, I received my very first home computer. That beautiful thing you see down there on the bottom left, the Atari 800 XL. What a wonderful machine that was. 64 kilobytes of RAM. That was a lot back in those days. Had these little wonderful shiny silver buttons on the right, and a really nice clicky mechanical keyboard. It was a wonderful, wonderful machine. And when you plugged it into your old big television, the wonders of being able to do things on the screen. And it came with two cassette tapes, because that's how we used to load programs back then, using a already unreliable medium for music. We loaded them and waited as things loaded on a cassette. And one of the cassettes that I received would change my life forever. And it was this cassette right here, an invitation to programming. And it was a marvelous thing that basically taught you the first principles of coding. Now, a lot of people in those days hadn't even seen a keyboard, so it started off by telling you, this is the return key, use this when you finished a line, and things like that, right through to here are how you, this is what a concept of a variable is, and here's the concept of a loop, and things like that. And actually, I reflected on it much over the following years as I fell in love with coding straight away, and those kind of first principles, I think, really helped to shape my coding knowledge going forward. So much of what I'm going to teach you now is based on how I learnt when I was 4 years old, and how I learnt those kind of first principles. Because whilst the programming language may have changed, and back then it was beginner's all-purpose symbolic instruction code, or BASIC. Now, obviously, you're using far more advanced things that are just as easy to use, things like Python and R and Java and C++. But the principles of coding have remained the same and continue to. So hopefully this sort of tutorial that you're doing this afternoon will give you the groundwork, so that when we start next week taking you through Python and introducing you to Python, we'll be showing you how to do this stuff in Python. Okay, so let's start right back at the basics. What is programming? So computers carry out instructions which are given to them by the user. And that's all a computer does. It just follows. A computer's rather stupid, essentially. It just waits for a user to tell it what to do. And we do that via instructions. And instructions are basically just a series of steps that the computer is going to work its way through. And what programming languages allow us to do is to communicate with the computer to provide it with these instructions, to say, I want you to do this, and then I want you to do that, and then I want you to do that. And we can write computer programs that essentially bundle up these sets of instructions to be executed when the program is run. So we give it a list of things we want it to do, and then we run the program, which means the computer will then go through and carry out those instructions. Let's talk a little bit about the computer architecture, because this is important to bear in mind, particularly when you're coding. Essentially, a computer architecture is made up of one or more input devices. These are things like, your keyboards, mice, etc. These are the ways in which we interact with the computer. And obviously these days we have things like touch screens and all that wonderful technology, but the principles remain that there are ways in which we can interact with the computer. And for coding, that means ways in which we can tell the computer what we want it to do to give it those instructions. And so the keyboard and the mouse remain and have remained for some time the primary ways in which we do that. We also have a central processing unit, or CPU. That's the central processor, which basically interprets the instructions that we give it, and it executes them. So we tell it what to do. The central processing unit interprets what we want it to do, and it will then go and order the computer to do it. We also have the concept of memory. And there are two different kinds of memory primarily. So memory is primarily used to store information that may be required later. Now that might be in the short term, in which case it's stored in RAM, which is random access memory. So that's kind of your short-term memory where things are stuffed there in order to for the computer to remember them, because it needs to access it whilst a certain program is running, but is then lost. Or it might be stuff that after we've closed the program or even shut down the computer, that we want to keep information, and then that would be on our storage. So things like hard drives, which retain information after that. So RAM is your sort of short-term memory, and hard drives and other storage devices are your longer-term memory, or indeed, if you want to go full retro, cassette tapes. Well, actually, if you want to go full retro, punch cards, but we won't go into that. And also, we've got one or more output devices, so things like monitors and speakers, which are essentially the way the computer communicates with you. That's the way in which the computer will take the outputs of the instructions that you've given it, and it will communicate those outputs back to you. So we've got ways in which we can give the computer instructions through our input devices, the central processing unit, which interprets and executes them, memory, which is used to store things that it needs to remember either in the short term or longer term, and output devices that communicate those outputs back to us. There are two kinds of programming language in the world. So there's things known as low-level programming languages. So these are things like assembly language. So this is basically, so an assembly language is where you're coding right down to the metal. And it used to be much more popular back in the old days when you did have only 64 kilobytes and processors that were 1 megahertz, because you had no resource to spare. You had to get right down there and basically tell the computer at a very low level, here's the registers that I want you to store this information in, and all that kind of stuff, and how to, I remember doing my computer science degree, and I remember a particular exercise where we had to write an assembly language, and the task was to get it to add two numbers together, and it took me the best part of 2 hours, and I still couldn't get it working. So I'm not a proponent of assembly language. It's very unique to whatever computer you're using, because you're basically giving the processor instructions directly, and you're giving it those very low level instructions. Most people these days we'll use high-level programming languages. And a high-level programming language is things like, in the old days, BASIC, but also C, C++, Java, Python, R, all these high-level languages. And basically what they do is they abstract from the details of the computer. So you as the coder don't need to worry about all of the register level, processor level stuff that's happening on your motherboard. All you need to worry about is how giving it sort of natural language instructions. So they use natural language. So if we want to print something to the screen, we can use the word print, and it will interpret that, and it'll the computer will then translate that into the low-level instructions that will cause it to output things onto a screen, and that makes programming a much more friendly and inclusive approach. So we're not going to be going into a low-level stuff in this course. It's only going to be high-level stuff, and a lot of these languages, whilst very different, share a lot of similarities, and the principles that you learn from one language are carried over to other languages. So you just learn essentially the vocabulary of how to do that stuff in a different language. Okay, so I mentioned something called variables right back at the start. So when we're coding, we often need to store information for use later, and we store that in the computer's memory. And usually that's in terms of variables, the short-term memory, so in the RAM. And essentially what we do is we organize that information into effectively boxes, and we call those boxes variables. And each variable has got a name and a value, and the name kind of indicates the information it's storing, and obviously the value, the actual information itself. So we might have a variable called forename, and I might put Dan, age 39, a bit higher than that now, and employee might be true. And this is all information that we can then access. So we're telling the computer, remember that my forename is Dan, remember my age is such and such. Okay, so that's all a variable is. But variables are at the heart of all coding, that you're storing information and then you use it later. And there are lots of different types of variables, depending on the kind of information that you're wanting to store. So a lot of times you're storing things like numbers, but there are lots of different ways in which you can store numbers. So we might have variables that are integers, which are whole numbers. And we might have floating point numbers, floats, and they're basically just numbers with decimal places. You might say, well, why do we have to worry about, having different types for integers and floating point numbers? It's all to do with memory. It's basically an integer takes a lot less memory to store, because it's a whole number, than a floating point number, which has a number of decimal places. And so we categorize things. If we don't need floating point precision, then we can just use integers for that particular variable, and it makes it much easier, more lightweight to store. There's also lots of different types of text that we can store. It might be individual characters, for example, so individual letters, numbers, or symbols, or it might be strings, sequences of letters, numbers, and symbols. And strings, in particular, you'll be using a lot during your coding journeys. We've also got Booleans. Booleans are basically variables that have two types of value, either true or false. And it's basically just a way of saying, is something true or is something false? And they're incredibly useful in coding, because we can just say that if that value is true, then do this. If that value is false, then do this. So they're really useful for conditional logic, which we'll come on to. There are also things called collections, and these are basically ways in which we can have more than one value collected together in a variable. So we can have things called lists, which are ordered sequences of things, which might be numbers or text or Booleans. We can have sets, which are the same things, but they're unordered and they're also unique. So a set will never contain duplicate values, and there's no importance to the order. It's just a collection of unique values. We can have dictionaries, which are unordered collections of pairs of index and value. So we can have a kind of lookup value and then a piece of information associated with that. And we'll go over all of these things in the Python tutorial. And we can have tuples as well, which are a bit like a list, but they can never change. And again, we'll talk more about that during the Python training. So let's say I wanted to build a simple calculator that just adds up two numbers. So basically, in programming terms, what we need to do is to tell the computer to first ask the user for the first number. Then we'd store that first number in memory as a variable. Then we'd ask the user for the second number. Then we'd store the second number in memory as a variable. So now we've got the computer remembering two pieces of information. And then we'd perform an addition operation. So we'd basically tell the computer, you need to take the two values I told you to remember, and then perform an addition operation. So get the processor to take one value and add it to the other. Then we'd store the result of the addition in memory as a variable itself. And then we display the result variable to the user. So that's basically what's happening. And if you were coding in assembly, that you'd have to do all of those things at a very low level. But because we're coding at high level, it makes it much easier to do all this stuff. So it's very rare that we write completely linear programs. Usually, for anything interesting, we want to change what happens depending on whether or not something else is true. And this is known as conditional logic. Basically, conditional logic allows us to say to the computer, look, if this is true, then I want you to do this. Otherwise, I want you to do that. So let's think about conditional logic. And a good way to think about it is to visualize it in terms of a decision tree. It's a really nice way to get your head around how conditional logic works. So I might have some conditional logic here that says, am I hungry? That will create a Boolean value, either true, I am hungry, or false, I am not hungry. It's usually true. Imagine if I'm not hungry, then maybe I do nothing. But if I am hungry, then do I have cake? If yes, then eat some cake. It's probably just going to be a standard, usually just going down that path there. But imagine that I don't have any cake. This is a disaster. Is the shop open? If it is, then go and buy cake. If not, eat something else, or possibly go to another shop. Sometimes, of course, we might have multiple initial checks to make on the original condition. It might not just be if this, then do this, if that, then do that. It might be there's multiple things we want to do. So it might be I ask the question, how many cakes do I have? So if I've got 10 or more, then I'm pretty safe for a moment, so I can probably get away with doing nothing. If I've got fewer than 10, but I've got at least 5, then maybe I want to start adding that to my shopping list, ready to purchase more cake. If I've got fewer than 5, but I've at least got 1, then I will walk to the shop because I'm going to need to buy some more, but I've got 1 to keep me going. If I've got none, then I need to run. I need to run to get that cake. So this is an example of where we've got multiple checks that we can make. So if it's this, then do this. But if it's this, then do this. If it's this, then do that. Otherwise, run. Another important concept in coding is the concept of a loop. So very often, we need the computer to do the same thing a certain number of times. So it might be that, for example, we have to do the same thing for a certain number of iterations, or we might need it to continue to do something while something else is true. And we use 2 different types of loop to achieve that. For the first one, we use something called a for loop. This is where we want it to say to do this thing this many times. For the second one, we use something called a while loop, which is where to say keep doing this until this becomes true. So let's have a look at a for loop. Let's say we want the computer to add 2 sugars to our cup of tea. So first thing we might want to do is count our spoons of sugar up to and including 2. Then I say, how many sugars have I added? If it's 2, then stop. If it's fewer than 2, I'm going to put a spoon in the sugar. I want it to scoop the sugar, add it to the tea, and then check it again. Now, how many sugars do I have? So the first time round, I've got 1 sugar. So I'm going to go around the loop again. This time I'll put the spoon in the sugar again, scoop it, add it to the tea. Now, how many sugars have I got? I've got 2, so I can stop. Okay, so this is a for loop where we're saying, keep doing this until you've reached the number 2, until you've got 2 sugars. So do this twice. And of course, we could easily adapt that to get some input from the user. So we could ask the user how many sugars they want. We could then store that in a variable called x, and then we could count the spoons of sugar up to and including x. So we would go around that loop here as long as we had fewer than x sugars in there, and then once we reached x, we would then stop. So a while loop is a little bit different. So let's say we wanted the computer to sing to us until we fall asleep. I'm not quite sure why you do that, but if you did, this is what you would do. So whilst the user is awake, keep doing this. First of all, check, is the user awake? If they're not, then you can stop. But if they are still awake, clear your throat, sing for a minute, hit them over the head. Are they still awake? If they are, go around again and keep doing that until they're no longer awake, at which point you can stop. Okay, so that's just a very quick sort of introduction to coding and to the main principles of coding, which are variables, conditional logic, for loops and while loops. And those 4 things make up most of the foundations of the basic programming. Okay, so what I'm going to ask you to do, I want you to start thinking in a coding kind of way, how you'd think about structuring things ready for code. So I'm going to put you into your groups, and I'm going to give you 45 minutes and have a 10-minute break on top of that as well. And you're going to have a go at this little exercise. So Chalk Showers and Baths, which is a division of Chalk Technologies, we're building a brighter future, has approached you to ask you to develop the software for a new automated shower system, the Chalk Automated Shower with Genius Responses and Banter Cash Grab System. So in this new system, the user steps into the shower and the shower asks them for their name. It then greets them with their name, saying good morning, good afternoon, etc., depending on what time of day it is. It then waits for the user to say begin, at which point the shower checks whether the user's got a previous perfect temperature stored. If they do, then it will turn on the shower at that temperature, and it will remain at that temperature until the user says too warm or too cold. If the user doesn't have a perfect temperature stored from previously, then what the shower will do, it'll turn on at 30 degrees, and the shower will continue to raise the water temperature by 2 degrees C every 5 seconds. If the user says too warm, the shower will drop the temperature by 1 degree C every 5 seconds. If the user says too cold, the shower will again start raising the temperature by 2 degrees C every 5 seconds. So it'll keep going up and down. It'll go up in bigger jumps than it goes down. If the user says perfect, then the shower holds the correct temperature and records it in a variable called perfect temp alongside their name in a variable called username, and it stores both of them in a list called user preferences. If the user had a previous perfect temperature, then their new temperature is overwritten. And obviously if they didn't, then this will be stored for the first time. Also, their calls of too warm, too cold, and perfect will work as described above. So if they step into the shower the next time, it'll turn on at their perfect temperature. But if they then said too warm, too cold, etc., it will start adjusting itself again. I mean, it's obviously, if this were made into reality, you'd probably want to check that your voice recognition system was pretty foolproof. At least you start scolding people as they can't hear, they understand somebody saying too warm, but there we are. So the shower will continue to run until the user says end shower, at which point the shower says goodbye, it's a friendly shower, followed by their name. So what I want you to do in your groups, I'm going to give you 45 minutes plus a 10-minute break to draw up an outline of the system. So what you should do in that is to draw a diagram outlining how the system will work, including any conditional logic, loops, variable storage, anything like that that's in that system. And I also want you to write a list of the variables that will be used in the system, along with the type of each variable. So refer back to your notes, refer back to the slides, and a short single sentence description of what the variable is storing. So obviously extract as much information as you can about how you think this will work. Feel free to be creative as well around this. And when we return, I'll spin the wheel and I'll get a couple of the teams just to show us what you've done. So basically you're going to draw up a kind of design for your program, how the system will work in terms of how it will be coded, where the conditional logic is, the loops, variable storage, etc. There's no, I'm not particularly interested in how you do that. You can draw it up however you like, however works best for you, as long as there's a clear description of how the system is going to work and clearly outlining conditional logic and loops and variable storage, etc. So however you want that to work in your groups, and then remember to write a list of the variables and describe what each one is doing, along with the type of variable. Any questions about any of that? Good. Okay. In which case, I will put you into your breakout rooms. So you'll have until 2:45, and then you can have a 10-minute break after that. So we'll resume here at 5:02, and off you go. I'll open up the breakout rooms now, and I will bounce around again. Continue to ignore me. I'm just listening in. And any questions, please shout. Hello, everyone. Okay, so welcome back. Hope that was, I was going to say, I hope that was fun. I forgot that I rather enjoy this exercise, and I rather enjoy it because it's one of these exercises which I think was quite amusing, dipping around to the different breakout rooms, hearing you all go through this, where at first you think this actually seems quite straightforward, and then realizing it's actually deceptively complicated once you start to try and unpick all this. So if you've thought that, you weren't alone. It's quite a common thing. In fact, I seem to remember giving this exercise to my colleague Kerry, who said that it's really deceptive, this one. So the key thing with this exercise is really to get you to try and think how you might structure a slightly complicated, deceptively complicated problem in a sort of programming kind of way. So it's to get you thinking about some of these structures, which you were all doing really well. So that's all good. Right, let me share my screen. I am going to leave off the ones that we selected this morning so far. They may get booted back in yet. We've got a little bit of extended time to take a few now. So I'm going to spin this wheel and let's see who is first up to present. Oh, it was just we got Johnny 5, state number 5 is today's winner. Okay, so someone from state number 5, do you want to share your screen? I'll stop sharing.
Yeah, I can do this. One of the challenges we had was how to actually present this. So bear with me a second.
Yeah, no worries.
We went down the word loop, the word route, got loops in the brain. Can you see this now? Hopefully you will do.
Yeah, that's all coming up.
Yeah, okay. If anyone else in the group wants to, they've got anything like what to add that I'm missing. So we've gone down an attempt of a flow chart, but we wait for user input. So if no one arrives, then we don't do anything. Step into the shower, ask for the name. If it's a new name, then we store that name. I've just highlighted in yellow where things get stored. We haven't put here is actually if we recognise the name, then we actually no, that's okay. No, we check the time, and then we give a message based on the time that was that we would check. So morning, afternoon, evening. The user activates shower, and they say begin. Check for perfect temperature based on the name. If there's one stored, then we go to this side, which is set to perfect temperature. And then we sit there and wait for any user input. So the user inputs are in red. Sorry, it's a bit messy. Too warm. So these 4 arrows coming off here. So if it's too warm, decrease temperature. Go back around waiting for user input. If it's too cold, increase temperature. Keep going around waiting for user input. If it's perfect, then we set the new perfect temperature and that gets stored. If the user says stop, then we turn off the shower and say goodbye, and it goes back to the beginning, waiting for the user. If there isn't a perfect temperature set, then it defaults to 30 degrees and then goes around this loop here. So it waits 5 seconds, it increases the temperature by 2 degrees, waits 5 seconds, and then will increase the temperature by 2 degrees again. It can only be, and then it can be broken by a user input, which feeds back in over here. So it's one of these options here. So if the user says too warm, then you can decrease temperature, and it goes back around these loops here. I think that's pretty much where we got to.
Great. That looks great. Yeah, thank you. That looks really good. I like your you get into that sort of mess in the middle where it's just like lots of loops and while loops, and that's the bit it's difficult to unpick.
Yeah.
So yeah, no, I could see that, but no, great. Really nice that you've organised that. So well, great. Okay, well, we've got a bit of time for maybe 1 or 2 more, so I'm going to spin the wheel again. Oh, I realised you can't see the wheel. Should have shared my screen. Okay, I will just tell you what the results are. It's Holly. Holly is the winner. You have to trust me. I honestly am not making that up. So somebody from the Holly team.
Yeah, I'll share. So we again struggled with how to display it, but we went down a flow route as well. Can you see my screen?
Yes, can see that.
So we've kind of put the steps in yellow, and then how the computer would kind of deal with that in the blue, and then the variables in the green. So again, we've got a kind of similar process with the shower asking for the name, and that coming from the variable storage. Then greeting the user based on a conditional time decision, so whether it's before or afternoon. Then another conditional step when the user says begin, and then again another conditional step about whether there's a perfect temperature stored or not. And again, sorry if this is really messy.
That's okay.
But yeah, using the perfect temperature if not, and then obviously if it says too hot or too cold, going through these while loops, or using the 30 degrees and increasing by 2 degrees, unless again the user input says too hot or too cold or perfect, and then stopping when the user says unshower, which is another conditional command there. And we are also kind of I don't know whether this is right or not, but we've suggested that they might need pre-stored variables of how much to increase or decrease the temperature by when there's a command. But yeah.
Brilliant. I like that idea of the pre-stored variables, because and that's something that you'll learn in the when we get into the actual coding, is that you very often don't want to hard code anything really. So obviously the spec says, look, it's going to increase by 2 degrees and it'll decrease by 1 degree per second, but actually, of course, they might change their minds. You don't want to hard code that. So they might say, actually, we're finding quite a lot of people are burning quite quickly. That's quite a steep increase. So that's a really nice idea to then sort of separate that out and have that so that you can change that really, really easily across your system. So yeah, really nice. Great, fantastic. Thank you. Okay, in which case we're okay for time, so we're going to do one more to spin the wheel. Let me share my screen so you can see it this time. Okay, let's spin. Ooh, yep, it's going to be Max. It's Max. Oh. There we go. Oh. You were going to get a round of applause, Max. Great.
I don't mind doing it. So, hang on. I mean, I don't think there's anything shockingly different to the other ones. Can you see it?
Yep, can see that.
So ours is person steps in shower, system asks their name and then stores the name. What time is it? I think you'd actually have more than the before 12, after 12, because you had etc. So there'd be like good night.
Yes,
things like
yes,
that as well.
I was hinting at that, yeah.
Yeah, but I think just for the sake of time, we stuck with that. But we talked about the fact you'd probably have to have other times and not just use the 12 o'clock as the way of measuring. So yeah, then it would be saying good morning or good afternoon or good night, and their name. And then it's waiting for them to say begin. And if they don't say begin, you do nothing. If they say yes, then we look at whether the name is stored on the system. And if it is stored, then it would be setting the perfect temperature, turning the shower on, and then waiting for the user command. If they say no, we had setting the temperature to 30 degrees centigrade, turning on the shower, automatically increasing it by 2 degrees every 5 seconds, unless it's interrupted by a user command. And then there were the 4 different user commands that we had. So too hot, too cold, end shower, perfect. So that's where we got to, and then we came back.
Fantastic, thank you very much. That looks great. So yeah, lots of really nice ways to represent that. Lots of using sort of flowchart style stuff as well, which makes a lot of sense. And hopefully that's enabled you to sort of get a bit of a grasp on the problem, which, as I say, was deceptively complicated. Okay, so let me reshare. Right, let's move on. So so we've talked about some of the basics of programming in terms of things like variables and conditional logic and for loops and while loops, etc. Another really important aspect of coding is the concept of functions. So usually when we're writing code, very often we want the computer to do things, and the things we want it to do, we'll probably want it to do again, either at different points in the program or even in a different program altogether. They might be quite common things that we want it to do. And now we could just keep telling it every time we want it to do it and give it all the instructions that it needs to follow. But that's quite time consuming, it's inefficient, and it's not a good way to program. So it's better if we got a common set of instructions that we need it to do all of the time, then we can bundle them up as what's known as a function. And a function basically is just a collection of instructions that we can call the function by its name and say, I want you, computer, to do this function, and it'll call that function and it'll say, okay, I'll go through and run that set of things. Now, a function takes inputs, doesn't have to, but most do in some way. It'll do something with those inputs, and then it will return an output. Could be multiple outputs. Very often it's just one. And the things that it does within the middle of it are just sets of instructions in the same way that you'd write anywhere in your code. And so we define a function by giving it a name. We tell it the list of inputs that it should expect, if any, the things we want it to do, and the outputs it should return, if any. Okay, so you normally do have some inputs and you normally do have at least one output. Not always the case, but typically. So you would typically have a function, you'd give it a name, you'd say, these are the things I want you to do something with, here's what I want you to do with them, and here's what I want you to throw back at me. Now, when we write a function in a computer program, unlike other instructions, where if we tell it to print something out to the screen, for example, or to follow a loop, it will do them as it reaches that point in the program. When we define a function, we're just telling the computer, here's what I want you to do when I call that function. I don't want you to do it yet. I just want you to remember that there's a function called whatever you've called it. And when I tell you to call that function, this is what I want you to do. But so it won't do it until you actually physically call that function. And that's a really important thing to remember, particularly if you're new to coding, that you'll sometimes you can get confused as to why, when you've written a function, why it doesn't do that automatically. And it's because what you're doing is you're telling the computer to remember this function. You're defining it, but you have to specifically say when you want it run. So our function, we have our function name, we've got our inputs that feed into that function, the stuff we want the function to do, and then it'll throw out some outputs at the other end. So as an example, we might have a function that we call find minimum, and this function may take 3 inputs, x, y, and z, and the objective of this function is basically to find the lowest of these 3 values. So our instructions might say set the value of x to be the variable lowest, so we default to x being the lowest value. Then we say is y lower than lowest. If it is, then now y becomes the value stored in lowest, and then we check if z is lower than lowest. If it is, then we set z to be the value of lowest. So we're looking through each one. We start assuming x is the lowest, and then we check y and z in turn to see if they're lower. And then once we get to the end of these instructions, it'll return whatever value is stored in lowest, and that will be the output. So then if we defined that function in that way, and then we called the function with these inputs, and we said, okay, computer, I want you to find minimum on 3, 7, and 2, it would return the value 2, because it would start by assuming 3 is the lowest, then it would check 7 and say, is that lower? No, it's not, so 3 is still the lowest. Then it would check the value of 2, that is lower, so now 2 becomes the lowest value, and that's the value that would be returned. Hand in hand with functions is another very important concept that you will, if you're writing anything beyond something fairly trivial or fairly experimental, then you're probably going to want to think about structuring your code in this way. And that's something that's called object-oriented programming, or OOP. So far, when we've talked about programming, we've talked about it as what's called the procedural programming methodology, which is basically where we say we give the computer a list of instructions, and it will then play out that list, and it will go through, I'll do that, and then I'll do that, and then I'll do that, etc. And that's fine, and that's how things used to work in the old days. In fact, when I used to learn BASIC back in the 80s, you had line numbers, and you'd say 10 print this, 20 go to 10, and you would specify very clearly that there's an order of things. But in modern programming, object-oriented programming is really, really important. So in object-oriented programming, basically everything is centered around the concept of objects. So everything becomes an object, and an object has its own attributes and methods. So attributes are basically variable values that are unique to that object, and it has its own methods, which are functions of that object. And basically objects are created as instances of what we call classes. And classes are basically like these generalized blueprints for how a certain type of object should work. Now I realize this probably doesn't make sense at the moment, so I'm going to explain this a little better by looking at an example. Okay, can somebody tell me what that is? It's not a trick question.
An ambulance.
An ambulance. Excellent. Good. You're very wary. I can tell. Are there any other answers to what that is?
A vehicle.
A vehicle. Excellent. Indeed. So you could say it is an ambulance. You could also say it's a vehicle, and both of those things are very true. So in object-oriented programming, if we refer to this as an ambulance, that might be an instance or an object. Okay, and a vehicle would be the class. So an ambulance is a type of vehicle. So a vehicle is kind of the class which has the blueprint for what this sort of thing should look like. And an ambulance is an example, an instance of that class that we can talk about specifically. So let's look at this example in more detail. So imagine we've got a class called vehicle. And as we said, all classes and all objects have attributes and methods. So attributes are variables and their associated values that belong to that particular object or class. And then we have methods, which are functions that make sense for that particular class or object. So the class contains the generalized description or blueprint. So we might have a class called vehicle, and it might have attributes. We've got 3 attributes here. One is the common name, which is a string type variable. That's where we store the name for it. The number of wheels, which we're going to store as an integer, whole number, and the capacity, which we'll store as an integer. So imagine we've got those three attributes, and we've got one method for our vehicle here, which is to drive at a certain speed, which we pass in as an input. So we've got three attributes and one method associated with the class of vehicle. And what we can do is we can create instances, a process known as instantiation, where we create examples of that class. And so we could create, and these things which are known as objects are basically examples, instances of this class. So we could create an object from this class of vehicle, and we could say, okay, I've got a vehicle here. Its common name is ambulance. It has 4 wheels and it has a capacity of 3. And I inherit the method of drive, but also particular objects may have their own methods as well. And this is something known as inheritance in object-oriented programming, where you inherit, this is known as the child, and you can inherit from the parent. So the child inherits all the stuff from the parent, but it may also have its own particular attributes or methods as well. So an ambulance may also have some methods that are specific to ambulances. I mean, these aren't good examples because you probably refill fuel on many vehicles. But to give you an example, so you might have fuel refill, activate siren, deactivate siren, load patient, unload patient. And some of those will be unique to ambulances. Some will be used in other vehicles, but not all. Whereas drive, we would expect on all vehicles. So here we've got another example. We've got common name bicycle. Again, this is an object that's an example of this blueprint class of vehicle, which has common name bicycle, number of wheels 2, capacity 1. Also inherits the drive method. This one's got its own little method here called repair puncture. And then here we've also got an inheritance, which is an object called car with 4 wheels, capacity of 5. Again, inherits the drive method and also has the fuel refill method. So all of these are objects. These are examples that take this blueprint of the class and then may add to it, but they all have their own unique instantiations. So in the class, there is no value. There's no common. There is no value for common name. It just says there will be a name. When you create an instance of this class, it will have a name. It will have a number of wheels, and it will have a capacity. And so when we bring these objects into being, we say you are a vehicle, and your common name is ambulance, and you have 4 wheels, and you have a capacity of 3, etc. So this is the blueprint, the class. These are the instances of the class, which are known as the objects. And this process is known as instantiation. Let's consider another example. Let's imagine we have a class called patient, and the patient has attributes with a name, which is a string, patient ID, which is an integer, and age, which is an integer. And it also has a couple of methods. So patients can attend DD and they can receive treatment. And then we create instances of this class, and these are the objects. So we can define in our code, here's what we mean by a patient, and then whenever we create a patient, we can say, okay, I've got a new patient here, his name is Bob Jones, this patient ID, this age, and again, takes these methods, but I've got another patient over here called Mary Smith with this ID and this age, and I've got another patient over here who's called Janet Small with this ID and this age. And so each time we create an object, we can just say, I want a new patient. We only define the patient once. And then each time we want a new patient, we can just say, I want a new patient. And it creates an instance of this class. And if we didn't do that, every time we want a new patient, we'd have to define what a patient is every time. So this allows us, is a shorthand for saying, I'm going to have this thing, this concept, called a patient, this entity type called a patient, and I'm going to create instances of that type, and then I can have lots of different patients with different names and IDs and ages. Now, when you create an object from a class, which is a process known as instantiation, there's something known as a constructor. And a constructor basically defines what happens when an object is instantiated from a class. So when you create an object from a class blueprint. And a good way to think about it is the constructor essentially constructing the object from that class blueprint, and the constructor will give the default values to the object, and it'll give the attributes and methods that it needs. And you write the constructor as a method within the class. Now, sometimes you don't have or you don't write a constructor in Python, for example. There's always one there. So if you don't write one, then essentially it will make a default assumption, and it'll just set it up exactly as it's specified in the class. But you should always, as good practice, write a constructor. And the reason being that you may, for example, let's say you create a patient, and let's say you want to give each one a new patient ID, you would then essentially set up your patient, and then the constructor would allocate that patient ID. So your constructor moves you from this blueprint, this general blueprint here, to the object here, constructs one of these made up from the blueprint specified in the class. So we don't specify it here, but always one of the methods will be the constructor. Any questions about any of that?
Yeah, go on then. I'm just thinking, your ambulance example, if you have like 5 ambulances, do you have kind of a hierarchy? Is like your vehicle your top class, and then ambulance, do you just then have 5 separate ambulances underneath it, or do you have another, is there like a class below that which is ambulance, which then has the 5 different ambulance objects?
No, so basically what you can have, so the first thing to say is you can have as many tiers as you want. So you could have a parent of vehicle, for example, and you could have a child of ambulance. So you can go up as much as you like with each child inheriting things from the parent. But generally speaking, for most of the stuff you do, you'll have a single class for a type of thing, and then you just create instances of that. So if you needed 5 ambulances, for example, in your model, then you just create 5 instances of this class, and usually you would do that in a sort of loop, and you'd say create 5 ambulances, and then you've got 5 separate objects that are all vehicles, but with all of these things as well. And then you can deal with them separately. So in the example of patients, so say you had to create 100 patients, you just write what a patient is once, and then you tell it to create, I don't know, 100 patients, and then you can follow each of those patients individually through your model, and they'll all have their own name and ID, and different things will happen to them. And you can set up, we talked about distributions earlier, so you can say in this one, actually this patient has this condition, and therefore they're more likely to spend longer with a nurse, or whatever it may be. But you're not having to define all that from scratch each time. You're just saying, this is what a patient is, and therefore I'm going to create lots of different types of patient with these properties. Does that make sense?
Yeah, I think so. Yeah, thanks.
So yeah, I mean, you're right. You can have multiple tiers. Don't worry too much about that. Particularly when you're first learning object-oriented programming, it's easier to think of a class and then objects, which are examples of that blueprint. That's the easiest way to think about it. But yeah, there's nothing stopping you having, for example, vehicle, and then you can have ambulances, and then you can have things that inherit from ambulances.
Right.
So you could have that as a class rather than an object, and you could say there's a class called ambulance which inherits from vehicle, and then you could create ambulances, and then you could also say I've got small ambulances, and that's a class, and you could go down as much as you want.
Okay, thanks. Yeah, that's what I was wondering.
Any other questions about that? No. Okay. First thing to say, I mean, object-oriented programming can be difficult to get your head around. So don't worry too much about it at this stage. You will get lots of practice at this. And when I take you through the Python stuff, we'll start just with the procedural programming, just to get you used to that. And then eventually I'll show you how to do object-oriented programming. And you'll find it's much easier than you think it is. Once you get the hang of it, it's actually quite straightforward. And once you start to think in that way, you'll find it much more natural. And one of the packages we show you, the discrete event simulation package, SimPy, there is a non-object-oriented approach that you can use, and we'll show you that first. And then there's an object-oriented approach that you can use. And you'll find that whilst the learning curve for the object-oriented approach is a little steeper, once you get the hang of it, you'll find it much easier and much more efficient for your models. But yeah, you'll have lots of practice of this, including now. So you get to practice some of these concepts. I know how much you all loved the original exercise, so I want you to go back to that exercise. Basically, you've been asked to ensure that your code for the cash grab shower system is object-oriented. So in your groups, I'm going to give you 40 minutes. Draw up some diagrams, and I want you to show what classes you think you'd include along with the attributes, including their types, so what types of variables you think you would store, and what types of methods for each of those classes. Okay, so what classes, what types of blueprint of things do you think you want in your cash grab system, and what for each of those classes, what would be the attributes, and for each one, what would be their type, and what would be the methods. And you should include a little short single sentence description of what each attribute and method does. And you should prefix it with the hash symbol there. If you're not already aware, that will become clear when we start teaching you actual coding next week. But put a little description. So if, for example, in this example here, where we looked at vehicle, so I've set up a class called vehicle. Here are my attributes, and here's the name of each attribute and the type. And here are the methods. I've only got one here. And then over here, I'm going to put a description of what each thing does. So common name stores a string representing the name of the vehicle type, such as car, motorcycle, etc. Number of wheels stores an integer that represents the number of wheels on the vehicle. Capacity stores an integer that represents the passenger carrying capacity. And drive method tells the vehicle to begin driving at the speed given as the input to the method. So a little description. So work out what your classes are going to be first, and then for each one, draw one of these, and then have some little descriptions which describe what these attributes and methods represent. Okay, so I'll give you 40 minutes, and then I'll call you back, and we will hear from a couple of the groups. Excellent. I will probably be resetting the wheel this time, so any of you may be asked to do it. Right, let me open the breakout sessions. Hi everyone. Okay, so welcome back. I had a really good listen to a lot of the groups there. Really interesting to see the different ways in which people are approaching it. There's a lot of similarities in terms of some of the classes that people are putting in, but really good to hear some of the discussions about which sort of methods would be needed and where, and that was kind of the purpose of this exercise, really. There's certainly no right answer, and it was really to get you to think about some of the considerations when you're trying to build in an object-oriented programming kind of way, and thinking about the various methods and attributes, etc. you'd use. So really good stuff that I was seeing. You'll get lots more practice as well in terms of object-oriented programming, because when we come to look at it in Python, I'll explain it again, and I'll be able to show you how you do this practically in Python, and hopefully that'll help it sort of fit into place. And you'll get again to practice it when you come to SimPy. In one of the SimPy sessions, and the agent-based simulation stuff is all based around object-oriented programming. So there's lots of opportunities to practice this. So this is just an early sort of get used to the principles kind of thing. Okay, so I'm going to ask a couple of groups to present for the last bit of today. I've put all the names back on the wheel, so you're all back in the frame now. So it could land on anyone. So let's spin the wheel, see who we've got first. Oh, I think it's going to be deep thought. Yeah, it's deep thought. Fantastic. Can someone from Deep Thought share what they've done, please?
Hi there. I'll share my screen where we got to. I think in terms of classes, we mainly thought into two classes. So we set one as the user and gave him attributes of name and preferred temperature. And to the user, we gave methods of entering the shower, leaving the shower, and then saying a command that it some way relates to their intention and based on the current temperature that they're receiving from the shower. And we did think whether for the other class, whether to separate out, for instance, say the sensing element or the timing element. We put most under shower. So we had as attributes an identifier for the shower and the model make, the current water flow states on or off, the default temperature that might come from the factory preset, current temperature, a current user that could be in the shower, a dictionary of greetings based on time of day, and some time from, say, GPS so that you can know if 5 seconds passed or not. And then some of the methods say hello greeting, which in some ways needs to take in the user that's in the shower, say goodbye greeting, fetch user's perfect temperature, toggle water flow, some to set and change temperature, record or sense voice commands, and then something to store perfect temperature. And then what we also weren't sure is, I guess what we did before with the flow, we have some master program for cache grab, that's the overarch control. Weren't quite sure whether that would be a method within the shower, whether that's some overarching master function overall.
Yeah, no, that's really interesting. So when you come to do this in reality, you'll find that, so normally what happens is you have a sort of series of modules, and you will essentially call in, so you will instantiate and have this sort of main class that basically controls everything else. So yeah, when you come to sort of do this in reality, you'll have something that sort of controls that. That sounds really good. I think that's interesting that you had a very similar debate to what many did around putting in the shower as a class, but then thinking whether there are aspects of the shower that need to be separated out. So you could have, a separate, you could think about and this is quite common in object-oriented programming, where you think about whether a class is trying to do too much or whether you need to break it down. So you might have, rather than a shower, you might have the different aspects of the shower in terms of the different control systems. You could have the voice control system and the temperature regulator control system, and the separated out like that as well. And very often, when it comes through sort of practice in designing this kind of stuff, and you're trying to keep your classes and your methods as kind of succinct as possible to do something very specific very well. So it's yeah, interesting, and as I say, no right answers for that. So excellent, thank you. That sounds great.
I realized I wasn't showing my screen as I was talking.
Oh, that's okay. Yeah, no worries. Okay, let me share my screen again. So let's spin the wheel again. I think it's going to be Skynet, is it? Yeah, looks like Skynet. Wait for the applause. Okay, great. Somebody from Skynet, do you want to share your screen?
Share screen. So we split into two classes. Can you see that?
Nope, it's not coming up.
Oh, sorry, 1 second.
That's it.
The person and the user or the shower. We initially discussed time at the beginning. We didn't get anywhere with it. So we gave them both an ID because we thought they might share. Sorry, the people we gave an ID. We gave a username, perfect temperature, and then we got a bit confused on the methods whether state should be the thing they are doing that would hold several commands, or whether each command should be a separate type of command. So yeah, so we wrote those out, and then we sort of had the same with the shower. We did ID, the current temperature, default temperature, which would be set to 30 for this example, but maybe it would be different in different countries. And then we had a sort of detect user, is someone in the shower, yes, no. And then we had methods to warm up, cool down, stop, start, greet the person. And then again, we thought maybe there'd be like a infrared, some way of detecting that the person has come in.
Fantastic. I love the I love the all the creative things that people were coming up with as I listened to the group. I ended up listening into one where you were putting in different languages, so we had a multilingual shower. There's another one that had a GPS system. It was just fantastic. I look forward to you all going away and designing these fantastic shower systems, which sound amazing. Yeah, I love the infrared. I mean, that would make sense. We said it detects when you get the shower, so there must be some way of doing that. So fantastic, excellent, great. Okay, let's do one more before we close off. Let's share again. Spin the wheel one more time. Yeah, it's going to be master control program. Okay.
You lucky lot have got me, so bear with me while I share.
Yeah, no worries.
So it's not too dissimilar to the previous two presentations, really. We've separated ours into two classes of user and shower. So under the user, the attributes have come up with the name and the perfect temperature, which are recorded against that user. And then there's two methods of the stop-start commands from the user to tell the shower to begin or cease the flow of water, and then the temperature commands to actually say whether or not you want to increase the temperature, decrease, or for the temperature to remain static. And then the shower itself, this got very ambiguous. Sort of, you know, do we go a bit more granular with this? Do we take each of these attributes out and give them a class of their own, really? But we went sort of high level with this one, really. So the attributes we chose were the current time, the current temperature, and the timer. And these represent the time of the day that the shower is in use, the current temperature of the shower. So during that flow rate, what is the current temperature versus the actual perfect temperature, which is assigned to the user. And then the timer, which is a countdown between the responses that the user gives, sort of 5 seconds between each response. And then our methods we discussed really with the flow of the water, whether or not the temperature would increase or decrease, again, that timer, and then the greeting given by the shower.
Fantastic, thank you. That looks great. And yeah, it's interesting that I deliberately kept this sort of very open, and I mean, I haven't even written a sort of model answer because I didn't want to prescribe anything. But it's interesting that a lot of you gone down very similar lines with this, and it's really good to see that you sort of latched on to the object-oriented kind of approach. So fantastic work, everyone. Really good. Okay, so that's the end of the lecture this afternoon, and also at the end of your first day of HSMA training. I hope you've enjoyed it. I appreciate there's been a huge amount of information that you've taken in today, so there's probably a lot to compute. I would strongly advise, as I would with all of these sessions, to have a look back over the notes when you know, give yourself a bit of resting time to rest, but have a flip back over the notes and just make sure that everything's sort of sinking in. So the next session will be on Thursday mornings. We've just got a half-day session on Thursday, and that's going to be the first session of the mini module, which is module 2. Basically, module 2 sort of runs in parallel to module 1. And in that module, we'll be taking you through basically free and open source development. So on Thursday morning, I'm going to show you how to use the coding tools that you will be using over the rest of the program, but particularly over the next few weeks, which is Spider and Jupyter Lab or Jupyter Notebooks, and also Google Colab. So I'll be giving you a bit of an intro. You'll have a bit of a play around with some code. You'll try some very, very simple coding stuff just to play around, but mainly to get you used to using these pieces of software and understanding how to interact with them ahead of next Tuesday's session, which will be the first of the introduction to programming in Python sessions. So you'll actually start writing your own code from next week. So I hope everyone's had a good day. Any questions, obviously, please do let me know. I will get these recordings up as soon as we can. They're going to need a little bit of editing, but we will get them up. But in the meantime, obviously, you do have access to the all of the materials, so please do look over that. Make sure you download the materials ahead of Thursday's session, and I'll also shortly be putting up the materials that you'll need for next Tuesday, so for the Python programming session. So make sure you read that carefully to make sure you've got everything downloaded ahead of that. Other than that, are there any questions before we close off? No? Fantastic. In which case, been a pleasure teaching you all today, and I will look forward to seeing you on Thursday morning for a bit of Spider, Jupyter Lab, and Google Colab. So until then, have fun and see you on Thursday, guys. See you later.
Thanks, Dan.